For humanity, life is a constant, strange game show, and the recent discovery of 3I Atlas has unveiled a cosmic menu of potential prizes. The choices are not simple. We are presented with door number 1, which holds the promise of groundbreaking scientific revelations that could fundamentally change our understanding of how planetary systems form. Or, we could choose door number 2, a more mundane option that simply confirms our current theories and adds a quiet footnote to our textbooks. But it is door number 3 that truly captures the imagination, a cosmic lottery with interstellar objects acting as the roulette ball. Each new visitor from beyond our solar system presents a fresh set of possibilities, some thrilling, some dangerous, and most, surprisingly ordinary. However, 3I Atlas is anything but mundane, and we have already catalogued a full spectrum of potential outcomes, from monumental discoveries to unsettling, headline-grabbing surprises. As we continue this exploration, we will uncover which of these scenarios is most likely to unfold in the coming months, and what the consequences could be for our understanding of the universe. The story of 3I Atlas began not with a bang, but with the silent click of a camera shutter, high in the Chilean mountains in the summer of 2025. On the night of July 1st, the asteroid terrestrial impact last alert system Atlas telescope captured something truly extraordinary, a celestial visitor that had journeyed for untold millions, or even billions, of years before briefly passing through our cosmic neighborhood. This object, now known as 3I Atlas, is the third confirmed interstellar object ever discovered, a silent witness to a completely different star system while the world went about its daily routine. This ancient wanderer was already racing toward our sun at an incredible speed of 57 kilometers per second. A velocity so immense it could circumnavigate the Earth in just 12 minutes. It is a speed that will eventually carry it out of our solar system forever, but its speed is not what makes it so unique. What truly defines 3I Atlas as a foreign entity to our system is its hyperbolic orbit. With an eccentricity of approximately 6 in the precise language of celestial mechanics, this means one thing: this object will never return. Unlike the comets that originate in our solar system, which follow predictable elliptical paths like cosmic boomerangs, 3I Atlas is on a path that bends around our sun but never closes. It came from somewhere entirely different, and it is heading to a place we can only guess at. The discovery process was a testament to the methodical and careful nature of modern astronomy. The initial detection was made on July 1, 2025. But a deeper dive into archived images revealed pre-discovery observations stretching back to June 1 for 2025, indicating that the object had been quietly announcing its presence for weeks before we finally noticed it. The official designation followed quickly, with 3I signifying its status as the third interstellar object, and Atlas honoring the survey that found it. This simple naming convention is a profound marker of our time, signaling that we now live in an era where visitors from other star systems are becoming common enough to warrant their own dedicated filing system. The trajectory of 3I Atlas is both unforgiving and precise. Its closest approach to the Sun, a point known as perihelion, will occur around October 29th to 30th, 2025, at a distance of about 1.36 to 1.4 astronomical units, which places it roughly 204 million kilometers from the Sun, somewhere between the orbits of Earth and Mars. For those concerned with potential risks, its closest passage to Earth will be in mid-December 2025, at a distance of about 1.6 to 1.8 astronomical units, approximately 270 million kilometers away. This is a distance greater than the closest approach of Earth and Mars. To be clear, there is absolutely zero risk of impact. The mathematics of orbital mechanics are well defined and leave no room for doubt with a trajectory so accurately measured. So, what exactly is this object we are observing? Early observations from the Hubble Space Telescope on July 21st revealed a familiar yet foreign sight, a teardrop-shaped dust coma, the classic signature of a comet being awakened by the sun's warmth. Initial size estimates suggest a nucleus no larger than 5.6 kilometers across, though it could be much smaller. It is not a mountain-sized chunk of ice and rock, but more like a large hill with a dramatic flare. However, as we are quickly learning, its size may be far less important than what lies within its ancient structure. We can confidently say that 3I Atlas is definitely interstellar, definitely active, and definitely safe. Its orbital class is confirmed, its activity level is measurable, and its distance from Earth is comfortably vast. But there is so much we do not know. We are still working to determine the exact size and shape of its nucleus, its detailed chemical composition, and, most compellingly, the specific stellar nursery where it was born. This uncertainty is not a failure of science, but rather the exciting frontier of discovery where our current knowledge meets a universe of possibility. The true significance of 3I Atlas lies in the fact that it carries within its frozen structure a chemical fingerprint from a completely different solar system. While the comets we are accustomed to were formed in our Sun's primordial disk 4.6 billion years ago, this visitor was born around a different star, under different conditions, and with different materials. It is a geological sample from a world we will never visit, delivered directly to our most sensitive instruments. Every molecule of water, ice, every grain of dust, every trace of carbon monoxide represents a valuable data point in the grand experiment of planetary formation. How do other star systems construct their worlds? What materials were abundant in the ancient galaxy? How similar or different are the processes that created our own neighborhood? 3.1. Atlas holds the potential to answer these questions, but only if we are clever enough to ask the right questions and sophisticated enough to interpret the data we gather. The name itself, Atlas, speaks to a deeper truth. This system was designed to find potentially hazardous objects that might one day threaten Earth. Instead, it found something that poses no threat, but offers something far more valuable: perspective. It is a reminder that we are not alone in this galaxy, not in the sense of little green men, but in the sense that planetary systems form, evolve, and occasionally share their cosmic leftovers across the vast expanse of interstellar space. As we continue this investigation, we must carefully separate what we know from what we hope, what has been peer-reviewed from what is still being debated, and what is scientifically sound from pure speculation. The truth about 3I Atlas is remarkable enough on its own, without any embellishment. We stand at a pivotal moment, watching an ancient traveler make a brief appearance in our cosmic backyard. The lessons it teaches us may reshape our understanding not just of comets, but of how planetary systems across the galaxy build themselves from the very dust of creation. The question isn't whether 3I Atlas will change everything, but rather how much and in what ways we are prepared to let it. The possibility of a major scientific windfall, an austere outcome, is at the forefront of our minds. What if everything we thought we knew about comets was wrong? What if the neat, tidy categories we have created, water-rich, carbon monoxide-enhanced, typical comets, were simply a limited perspective, born from our experience with objects from only one star system? 3I Atlas is already forcing us to rewrite the textbooks in real time. The first major revelation came from the James Webb Space Telescope, JWST, humanity's most advanced eye in space. Its near-infrared spectrograph detected something that made astronomers question their instruments: unusually strong carbon dioxide emissions relative to water. Early data suggests a staggering ratio of 8 parts carbon dioxide for every 1 part water vapor. For context, typical comets in our solar system show the exact opposite pattern, with water being the dominant chemical. This finding is not just unusual, it is extraordinary. But the surprises did not stop there. The Spherix mission, designed to map the entire sky in infrared light, also observed 3I Atlas and discovered something even more puzzling. The carbon dioxide coma, the cloud of gas and dust surrounding the nucleus, extends for at least 348,000 kilometers, a distance nearly as vast as that between the Earth and the Moon. In those same observations, water and carbon monoxide, the substances that usually signal a comet's activity, were not detected. We must approach these findings with the appropriate scientific caution. These are preliminary results, the kind that make scientists both excited and nervous. The teams analyzing this data are still refining their measurements and double-checking their calibrations. We are witnessing the messy, iterative process of science in action, where raw data is slowly transformed into understanding. Yet, even with this caution, the implications are staggering. The dominance of carbon dioxide suggests 2 primary scenarios, both with profound consequences for our models of planetary formation. The first possibility is that 3I Atlas was formed beyond the carbon dioxide ice line in its home star system. In the frigid outer reaches where carbon dioxide freezes before water does, this would place its birthplace in a region equivalent to our own outer asteroid belt or beyond, in a cold, dark place where only the most volatile substances remain gaseous. The second possibility is that the nucleus has developed a surface crust that effectively suppresses the sublimation of water, while allowing carbon dioxide to escape. Think of it as a cosmic thermos bottle with an outer layer that insulates the interior and controls which materials can outgas when heated by the sun. Both of these scenarios force us to fundamentally reconsider how protostellar disks distribute their chemical ingredients. We are not just looking at one weird comet. We are potentially glimpsing an entirely different approach to building worlds. The coordination of observations across multiple facilities has been a masterclass in modern astronomy. The JWST provides the detailed molecular fingerprints through its near-infrared spectrograph, while the Hubble Space Telescope captures the morphology and size constraints with its incredible resolution. Spherix maps the extended environment with wide-field spectral coverage, and ground-based telescopes at the Gemini Observatory and Noy Lab add complementary imaging and spectroscopy. Each instrument sees something different, but together, they are assembling a portrait of an object unlike anything in our solar system's family album. This comparative context makes 3I Atlas even more intriguing. 2I Borisov, our previous interstellar comet visitor, behaved like a perfectly normal comet, water-dominated, predictable, and familiar. It fit comfortably into our existing understanding of how comets work. 1I ʻOumuamua, our very first confirmed interstellar visitor, was so unusual that astronomers are still debating whether it was a comet at all. Some evidence suggested it might have been more of an asteroid, or something else entirely. 3I Atlas fills a crucial gap in this small but growing catalog. It is definitely a comet, with its characteristic dust coma and outgassing, but it is a comet unlike any we have ever seen, a messenger carrying a story from a distant star system. The mysteries it presents are not just puzzles to be solved, but invitations to expand our cosmic perspective and reevaluate our place in the galaxy. There is no doubt that this celestial visitor, a comet unlike any we have ever seen, challenges our fundamental assumptions about what is normal. In the broader context of the galaxy, the scientific payoff from this one object extends far beyond the narrow field of comet science. The peculiar volatile ratios that 3I Atlas is revealing are helping astronomers pinpoint the birth zones and reconstruct the thermal histories of protoplanetary disks across the galaxy. Every star system builds itself differently, using a unique mix of raw materials and following the specific dynamics of mass, temperature, and time. By meticulously studying the chemical signatures of these interstellar visitors, we are essentially conducting cosmic archaeology on planetary formation processes that happened billions of years ago around stars we will never visit. The enduring data legacy of this event deserves special attention. Unlike transient phenomena that disappear forever, astronomical datasets often improve with age. The raw images and spectral data being collected right now will be reanalyzed for decades to come. As calibration techniques become more sophisticated and new analysis methods are developed, organizations like NASA and ESA will maintain open archives specifically for this purpose, ensuring that today's observations become tomorrow's groundbreaking discoveries. This global observational campaign represents coordination at its finest. Observing windows have been carefully orchestrated to maximize scientific return. Even though Earth will be poorly positioned during the comet's perihelion when it swings closest to the Sun, spacecraft scattered throughout our solar system will pick up the observations when ground-based telescopes lose their view. This creates a continuous, unbroken record of the comet's evolution. The theoretical implications of this discovery are rippling outward like waves from a dropped stone. If 3I Atlas truly originated in the galactic thick disk, a population of older metal-poor stars formed during the galaxy's youth, then we are examining material that predates Earth's formation by billions of years. We would literally be holding a piece of cosmic history in our scientific instruments, a sample from an era when the universe was fundamentally different. However, we must be honest about the controversy that surrounds this. There is active debate about whether 3I Atlas comes from the thick or thin disk, whether its parent system was ancient or relatively recent, and whether its unusual chemistry represents primordial conditions or later evolution. Science thrives on such disagreements, using them as fuel for better observations and more sophisticated analysis. The ultimate jackpot here is not spectacle, but precision. While the general public might be hoping for dramatic photos or a brilliant tail display, the true treasure lies in the sharp chemical signatures and precise dynamical measurements that will help constrain our models of how planetary systems form across the galaxy. Every spectral line, every velocity measurement, every photometric data point represents a piece of evidence in the grand jury trial of planetary formation theory. 3I Atlas is teaching us that our solar system, for all its familiarity, represents just one of countless approaches to building worlds from cosmic dust. Other stars, other systems, and other approaches exist, and occasionally, if we are very lucky and very prepared, those other approaches come to visit us. The question is no longer whether interstellar objects will revolutionize our understanding of planetary formation. The question is how quickly we can learn to read the messages they carry. Sometimes, the most profound discoveries happen not because we build something new, but because we are clever enough to point existing tools in the right direction at precisely the right moment. The beauty of 3I Atlas lies not in the fact that it requires some massive new space mission, though that would certainly be exciting, but in how it perfectly aligns with humanity's existing scientific infrastructure. We do not need to spend billions of dollars or wait decades for new launch windows. We just need to be smart about coordination and opportunistic about our timing. The reality of modern astronomy is that the most capable instruments are already in space, already operational, and already delivering groundbreaking science on a regular schedule. The James Webb Space Telescope JWST is revolutionizing infrared astronomy. The Hubble Space Telescope continues its legendary service despite decades in orbit. The Spherix mission is mapping the entire sky. The challenge is not building new capabilities. It is orchestrating the ones we already have. And the orchestration for 3I Atlas has been remarkable. JWST can pivot small fractions of its observing time toward the comet during key windows, using its unparalleled infrared sensitivity to dissect molecular emissions with unprecedented precision. Hubble adds its legendary resolution for morphology studies and size constraints. Spherix contributes wide-field spectral mapping that captures the extended environment around the nucleus. On the ground, this coordination extends across continents. The Gemini North and South observatories provide complementary observations from both hemispheres, while the Palomar Observatory adds its own unique perspective. NOILAB coordinates across multiple facilities to ensure comprehensive coverage. But here is where things get even more interesting. Some of the best observations might not come from Earth at all. Spacecraft scattered throughout the solar system find themselves in uniquely advantageous positions. During 3I Atlas's passage, the ESA's JUICE mission, fresh from its August 31st Venus gravity assist, will be approximately 68 million kilometers from the comet during key observation windows. NASA's Psyche spacecraft, currently en route to its metallic asteroid target, sits roughly 45 million kilometers away. Even the Mars orbiters, including NASA's Mars Reconnaissance Orbiter, China's Tianwen-1, and the UAE's HOPE mission, enjoy front-row seats at distances of just 29 million kilometers. These are not purpose-built comet missions. They are existing spacecraft with their own primary objectives, carefully planned timelines, and scientific priorities. But geometry and timing have aligned to offer unprecedented opportunities for multi-platform observations of an interstellar visitor. The advantages of these spacecraft observations become crucial around perihelion, when Earth's view of 3I Atlas becomes severely compromised by the Sun's overwhelming glare. While ground-based telescopes lose sight of the comet behind the Sun's brightness, spacecraft positioned throughout the solar system can maintain a clear line of sight. They can watch the comet's tail develop, monitor its outgassing behavior, and potentially even sample dust particles if orbital mechanics align favorably. These observations are not guaranteed. They are opportunistic. The instruments on these spacecraft are not necessarily optimized for comet science, and their primary mission requirements always take priority. However, even modest resolution imaging and basic spectroscopy from these platforms could provide invaluable data about how 3I Atlas behaves when it is impossible to observe from Earth. The public engagement potential of this event also deserves significant recognition. Live-streamed observing sessions, particularly from major ground-based facilities like Gemini South, have proven enormously popular for previous interstellar visitors. Citizen science projects that allow the public to participate in data analysis add another layer of engagement. When the general public can directly contribute to cutting-edge science, it transforms abstract research into a personal investment. Behind the scenes, 3I Atlas is driving technological improvements that will benefit all future astronomy. The observation of such a fast-moving target requires more sophisticated tracking algorithms, faint objects demand better noise reduction techniques, and cross-facility coordination needs robust data-sharing protocols. Each of these challenges pushes the boundaries of what is technically possible, creating solutions that will benefit far more than just comet science. The data tooling upgrades are particularly significant. Better pipelines for processing observations of moving targets will improve asteroid surveys, planetary mission operations, and space situational awareness. Enhanced cross-calibration between JWST's Spherex and Hubble creates more reliable photometric standards for all astronomical observations. These are not just improvements for this one comet. They are infrastructure upgrades for the entire field. Future mission concepts are already incorporating lessons learned from the 3I Atlas observations. The Comet Interceptor mission represents a new philosophy. Instead of launching toward a specific target, position a spacecraft at a gravitationally stable point and wait for interesting objects to announce themselves. 3I Atlas validates this approach by demonstrating both the immense scientific value of interstellar visitors and the practical challenges of late discovery and high velocity. A reality check on the budget is crucial here. This entire scientific windfall does not require congressional appropriations or multi-year development programs. It is primarily a matter of coordination, scheduling, and data sharing among existing facilities. The most expensive component might be the extra staff time needed to analyze the resulting datasets. This is not to minimize the complexity. Coordinating observations across multiple space agencies, ground-based facilities, and spacecraft missions requires immense diplomatic finesse and technical precision. Time on premier facilities like JWST and Hubble is extraordinarily valuable, allocated through highly competitive processes months or even years in advance. Pivoting even small amounts of observing time toward 3I Atlas represents a significant commitment, but the return on investment is extraordinary. For relatively modest coordination costs, humanity gains its most comprehensive look yet at material from another star system. We develop new techniques for the rapid response observation of transient targets. We demonstrate international cooperation in real-time science, and we inspire the next generation of scientists and engineers. The lesson extends far beyond this single comet. In an era of increasingly expensive flagship missions and decade-long development cycles, 3I Atlas demonstrates the continuing power of smart coordination among existing assets. Sometimes the most profound discoveries do not require the newest, biggest, most expensive tools. They simply require the wisdom to use what we already have most effectively. As we watch this coordination unfold, we are witnessing a preview of how science will work in the era of routine interstellar visitors. The infrastructure is largely in place. The techniques are being refined. The international cooperation frameworks are being tested. 3I Atlas is not just a comet. It is a proof of concept for 21st century astronomy. However, Not every cosmic visitor arrives with a grand fanfare. Not every scientific breakthrough comes wrapped in spectacle and social media buzz. Sometimes, the most profound discoveries happen quietly and methodically, without disrupting anyone's weekend plans or inspiring Hollywood blockbusters. This is the most likely scenario for 3I Atlas, and that is perfectly fine. The geometry of the situation works against a dramatic, visible display. When 3I Atlas passes closest to the Sun, the glare will make it difficult to observe from Earth. As 3I Atlas passes through the innermost parts of our solar system, reaching perihelion in late October 2025, Earth will be poorly positioned to observe it. The comet will be lost in the Sun's glare, a ghost in the sky, invisible to casual observers and accessible only to a specialized network of spacecraft and carefully planned professional observations. There will be no naked-eye spectacle, no social media frenzy, and no brilliant tales stretching across the sky. Instead, there will be data sets, a quiet torrent of information collected by dedicated instruments. The observational cadence itself tells a story, a period of intense monitoring as the comet approaches, followed by a gap in which Earth-based observations become impossible, and then resumed observations in December as 3I Atlas emerges from behind the Sun's glare. This structured process dictates what we learn and when we learn it, creating a natural progression from initial characterization to post-perihelion analysis. During the solar gap, spacecraft positioned throughout the solar system will continue their work. Mars orbiters will monitor the comet's behavior when it's closest to the Sun. Deep space missions will track its tail development, and solar observatories will capture its intricate interaction with the solar wind. The data collection never stops, it simply shifts platforms. For most people, this event will feel like a non-event, a subtle blip on the cosmic radar. News coverage will be respectful but restrained, focusing on scientists study distant comet, rather than death from space, narrowly avoids Earth. Educational institutions will incorporate 3I Atlas into lesson plans about the solar system and the scientific method. Space agencies will publish regular updates with measured language about scientific progress and international cooperation. This measured response represents healthy scientific communication. 3I Atlas is genuinely fascinating to scientists and profoundly important for our understanding of planetary formation, but it will not fundamentally alter daily life for anyone outside the astronomical community. The story is one of a safe, distant, and beautiful dataset rather than a once-in-a-lifetime sky event. The quiet nature of this outcome creates a unique space for genuine scientific education. Without the distraction of sensationalism or crisis framing, there is room to explain how uncertainty works in science, how preprints differ from peer-reviewed papers, and why patience is essential to discovery. These are crucial lessons for scientific literacy, but they are often overwhelmed by more dramatic narratives. The educational value of watching science work normally cannot be overstated. The public can follow along as initial observations are refined, as preliminary results undergo peer review, and as competing hypotheses are tested against new data. This is how science actually functions, not through sudden paradigm-shifting announcements, but through the careful accumulation of evidence and the gradual refinement of understanding. The professional community benefits enormously from this approach. Cross-validation between different instruments and facilities can proceed without external pressure. Negative results and non-detections get appropriate attention rather than being dismissed as boring. Long-term studies can develop without the constant distraction of public explanations and media management. From a policy perspective, a quiet outcome supports steady, sustainable funding for astronomical surveys rather than the boom and bust cycles driven by fleeting public excitement. Programs like ATLAS, LINEAR, and the upcoming Vera C. Rubin Observatory need consistent support over decades to function effectively. Sensational events can trigger short-term funding increases, but they can also create unrealistic expectations about the pace and nature of discovery. The cultural impact, though subtle, may be more profound than immediate spectacle. 3.1. Atlas normalizes the idea that our solar system is not isolated, that material moves between star systems, and that we live in a galactic neighborhood where visitors occasionally stop by. This represents a fundamental shift in how humanity thinks about its cosmic context, but it is the kind of shift that happens gradually, through accumulated awareness rather than sudden revelation. For astronomers, the quiet outcome allows them to focus on what matters most: the data, without media circuses or public pressure for immediate results. Research teams can take the time needed for proper calibration, thorough analysis, and careful interpretation. The resulting papers will be more reliable, more comprehensive, and more useful for future research. The long-term scientific value often exceeds the immediate impact. Data sets from 3I Atlas will be archived and reanalyzed for years to come as techniques improve and new questions arise. Today's preliminary results become tomorrow's refined measurements, which become next year's theoretical insights, and ultimately, next decade's textbook examples. This pattern repeats throughout astronomy. Many of the most important discoveries in the field were initially unremarkable, catalogued objects that became crucial years later when better analysis techniques revealed their significance. pulsar timing arrays, gravitational wave detection, and exoplanet discovery all followed this pattern of quiet accumulation, leading to revolutionary understanding. The international cooperation aspect continues regardless of public attention. Scientists from different countries and institutions will collaborate on data analysis, instrument calibration, and theoretical interpretation. These professional relationships strengthen the global scientific community and establish frameworks for future discoveries. Data sharing protocols developed for 3I Atlas will benefit other moving target observations. Rapid response coordination techniques will improve our ability to respond to future interstellar visitors. Cross-facility calibration methods will enhance all astronomical observations involving multiple telescopes. Even in the quiet scenario, citizen science opportunities will remain available. Image processing projects, data validation tasks, and educational programs can engage interested members of the public without requiring mass participation or media attention. Quality over quantity often produces better results in citizen science contexts. The absence of drama does not mean the absence of discovery. Some of the most significant advances in our understanding of planetary formation, stellar evolution, and galactic structure have come from the careful analysis of unremarkable objects. 3I Atlas could easily fall into this category. Scientifically crucial, but publicly invisible. Perhaps most importantly, the quiet outcome allows 3I Atlas to establish baselines for future interstellar visitor studies. The observational techniques, analysis methods, and coordination protocols developed for this object will inform our responses to future visitors when the discovery timing, geometry, or characteristics might be more favorable for public engagement. The gap between expectation and reality matters here. Managing public expectations appropriately, emphasizing scientific value over visual spectacle, creates a healthier relationship between professional astronomy and public understanding. Science communication works best when it is honest about what to expect and why it matters. In the end, the quiet path scenario represents science at its best. Careful, methodical, international, patient, and focused on understanding rather than entertainment. Not every cosmic event needs to be a blockbuster. Sometimes the most valuable discoveries happen when scientists can work without distraction, building knowledge step by careful step. The universe is full of quiet wonders, and 3I Atlas may be one of them. Now, let's address the cinematic worst-case scenarios and why they are simply not on the table. In our age of social media panic and fantastical disaster movies, the questions inevitably arise. Can 3I Atlas destroy Earth? Can it trigger solar flares? Can it somehow hide behind the sun and launch a surprise attack? The short answer is an unequivocal no. The long answer involves some very satisfying mathematics that demonstrates exactly why these fears are not just unlikely but physically impossible. Let's start with the impact scenario, as that is usually everyone's first concern. 3I Atlas will approach no closer than approximately 1.6 astronomical units from Earth, which is roughly 270 million kilometers. To put this into perspective, this is farther than the distance between Earth and Mars at their closest approach. Worrying about an impact is like worrying about a car accident when the other vehicle is in a different time zone. But let's be more precise. The gravitational influence of any object falls off as the inverse square of the distance. At 270 million kilometers, 3I Atlas, even if it were somehow much larger and more massive than current observations suggest, would exert less gravitational pull on Earth than a large building exerts on you when you walk past it on the street. The gravitational chaos myth deserves special attention because it sounds almost scientific. Could 3I Atlas somehow disrupt planetary orbits or destabilize the solar system? The mathematics are brutal in their clarity. Even if 3I Atlas were 1,000 times more massive than current estimates, its gravitational effect on planetary motion would be utterly negligible. Consider the mass ratios involved. Earth weighs approximately 6 times 1,024 kilograms, Jupiter weighs about 318 times more than Earth, the Sun weighs about 330,000 times more than Earth. 3I Atlas, generously assuming a 5 kilometers radius and a typical comet density, weighs perhaps 1,014 kilograms. That means Earth outweighs 3I Atlas by a factor of roughly 60 billion to 1. The idea that this tiny iceberg could meaningfully perturb a planet is like suggesting that a mosquito could deflect a freight train by flying into it. The doomsday tail scenario requires its own mathematical reality check. Comet tails consist of incredibly tenuous gas and dust, far less dense than the best vacuum we can create in terrestrial laboratories at astronomical distances. Even passing directly through a comet tail poses no meaningful threat to a spacecraft, let alone a planet. The material is so diffuse that you could compress the entire tail into a sphere, and it might weigh less than a car. Moreover, 3I Atlas won't come anywhere near Earth. Its tail, no matter how spectacular it might appear in photographs, consists of particles following slightly different trajectories than the nucleus itself. These particles will disperse across millions of kilometers of space, creating a beautiful but utterly harmless display for any spacecraft positioned to observe it. Finally, for the truly creative conspiracy theory, that it is hiding behind the sun to attack. This myth demonstrates a fundamental misunderstanding of both orbital mechanics and the nature of our observations. 3i. Atlas is not hiding. It is following a predictable trajectory calculated from hundreds of observations by dozens of facilities worldwide. The solar conjunction period, when Earth-based observations become difficult, is a consequence of geometry, not strategy. During this period, spacecraft positioned throughout the solar system will continue to observe it. Providing an unbroken data record, we know exactly where it is and where it is going. The fear-mongering and sensationalism often found in media and online platforms are not based on science, but on a lack of understanding. The physical impossibility of these scenarios provides a great opportunity to educate the public about the actual scale and dynamics of our solar system. The universe is a vast and mostly empty place, and the distances involved in these celestial passes are immense. The true danger lies not in distant harmless comets, but in a lack of scientific literacy and the propagation of misinformation. By patiently and clearly explaining the real science, we can replace fear with fascination and empower the public with knowledge. 3i. Atlas is a guest, not a threat, and its visit is a precious gift of scientific data that will enrich our understanding of the cosmos for years to come. During 3i Atlas's passage, the fear-mongering and sensationalism often found in media and online platforms are not based on science, but on a lack of understanding. The physical impossibility of these scenarios provides a great opportunity to educate the public about the actual scale and dynamics of our solar system. The universe is a vast and mostly empty place, and the distances involved in these celestial passes are immense. The true danger lies not in distant, harmless comets, but in a lack of scientific literacy and the propagation of misinformation. By patiently and clearly explaining the real science, we can replace fear with fascination and empower the public with knowledge. 3i. Atlas is a guest, not a threat, and its visit is a precious gift of scientific data that will enrich our understanding of the cosmos for years to come. Mars, orbiters, deep space missions, and solar observatories will continue monitoring its behavior. There is no concealment, no surprise capability, and no strategic positioning. There is just a comet following Newton's laws of motion with clockwork precision. The size mythology needs addressing, too. Early media reports occasionally conflate brightness with size, suggesting that 3i Atlas might be much larger than current estimates indicate. But brightness depends on surface area, reflectivity, and outgassing activity, not just size. A small, highly active comet can appear brighter than a large dormant one. Current observations constrain the nucleus to no more than about 5 to 6 kilometers across and possibly much smaller. Even if 3i Atlas were larger than estimated, size alone doesn't create danger at these distances. A 10 kilometers comet at 270 million km is still utterly harmless to Earth. It's like worrying about getting wet from a water balloon thrown from the next state over. Let's establish an evidence standard for the rest of our investigation. Peer-reviewed papers carry the most weight, followed by preprints that are undergoing review, followed by conference presentations and press releases. Extraordinary claims require extraordinary evidence, and the more extraordinary the claim, the higher the evidence bar should be. NASA's official communications about 3i Atlas consistently emphasize its safe distance and predictable behavior. These are not bureaucratic cover-ups or attempts to prevent panic. They're accurate summaries of what the orbital mechanics actually show. When space agencies around the world agree on basic facts like trajectory and closest approach distance, those facts are extraordinarily reliable. The scientific community has developed sophisticated methods for detecting and characterizing potentially hazardous objects. The same surveys that found 3i Atlas routinely identify and track asteroids and comets that could pose genuine risks to Earth over timescales of centuries. These systems work, they're constantly improving, and they're operated by people whose careers depend on accuracy. Media literacy becomes crucial here. Headlines designed for clicks don't always reflect the content of the articles they introduce, and articles don't always accurately represent the scientific papers they discuss. The most reliable information comes directly from space agencies, major observatories, and the scientists actually conducting the observations. Visual effects in movies and television create unrealistic expectations about how space objects behave. Real comet tails are usually invisible to the naked eye, extend in directions determined by solar wind rather than orbital motion, and consist of material so tenuous that it barely qualifies as matter at all. Real asteroid impacts require very specific size and velocity combinations to cause significant damage. Real orbital mechanics follow predictable mathematical rules that don't allow for dramatic last-minute course changes or surprise attacks. The myth-busting isn't meant to dismiss curiosity or discourage questions. Healthy skepticism and scientific inquiry go hand in hand, but they work best when directed toward understanding what is actually happening rather than imagining what might be happening if the laws of physics worked differently. Here's our promise for the rest of this investigation. We'll clearly distinguish between peer-reviewed results, preliminary findings, and speculative possibilities. We'll show our work when we make claims about distances, masses, and energies. We'll acknowledge uncertainty when it exists and avoid certainty when it doesn't. 3. Atlas offers plenty of genuine mysteries worth exploring. We don't need to invent fictional dangers to make it interesting. The truth about this interstellar visitor is remarkable enough without embellishment, and threatening enough to our preconceptions without being threatening to our planet. Mathematics doesn't lie. It doesn't exaggerate for dramatic effect, doesn't hedge its bets for political reasons, and doesn't care about our hopes or fears. When we apply the cold, precise language of orbital mechanics to 3I Atlas, the story it tells is both reassuring and illuminating. Let's start with the fundamentals of what makes an orbit hyperbolic. Every orbit has an eccentricity, a number that describes how stretched or circular the path is. Circles have an eccentricity of 0. Ellipses have eccentricities between 0 and 1. Parabolas have an eccentricity of exactly 1. And hyperbolas, the mathematical curves that describe escape trajectories, have eccentricities greater than 1. 3I Atlas has an eccentricity of approximately 6. This is not a measurement uncertainty or a preliminary estimate subject to revision. This is a fundamental characteristic determined by hundreds of precise position measurements from multiple observatories worldwide. An eccentricity of 6 means the object is moving far too fast to be captured by the sun's gravity. It came from interstellar space. It will return to interstellar space, and there's nothing in our solar system massive enough to change that fact. The velocity at infinity, the speed 3I Atlas would maintain if it were traveling through empty space far from any gravitational influences, is approximately 57 to 58 kilometers per second. This is its cosmic baseline speed, the velocity it carries as a relic of its formation and ejection from another star system. When combined with the sun's gravitational influence, this velocity determines every aspect of 3I Atlas's trajectory through our solar system. That inbound trajectory traces back to the constellation Sagittarius, not because 3I Atlas originated there recently, but because that's the direction it was traveling when it entered the sphere of the sun's gravitational influence. The actual journey from its birth star to our solar system likely took millions of years and involved a much more complex path through the galaxy's gravitational landscape. Here's where the mathematics becomes simultaneously elegant and reassuring. Once 3I Atlas entered our solar system, its entire future path became precisely predictable. Newton's laws of motion and gravity don't allow for surprises, course corrections, or dramatic last-minute changes. Every spacecraft navigation team in the world can calculate this trajectory to extraordinary precision, using equations that have changed since the 17th century. Even if 3I Atlas was somehow equipped with rocket engines and guidance systems, which it emphatically is not, the energy required to alter its course enough to threaten Earth would be beyond anything humanity has ever built. Planetary deflections during the passage are real but minuscule. As 3I Atlas swings past the Sun, it will experience gravitational influences from Jupiter, Saturn, and the other planets. These influences will slightly modify its outbound trajectory, changing its direction by fractions of a degree and its speed by meters per second. But the fundamental character of the orbit remains unchanged. Hyperbolic in, hyperbolic out. The closest approach to Earth occurs in mid-December 2025 at approximately 1.6 to 1.8 astronomical units, roughly 270 million kilometers. At this distance, 3I Atlas exerts less gravitational force on Earth than Earth exerts on the International Space Station. The tidal effects are so negligible they fall below the threshold of measurement by our most sensitive instruments. To understand why, consider the mathematics of tidal forces. These forces depend not just on mass and distance, but on the gradient of gravitational field strength. The Moon creates noticeable tides on Earth because it's relatively close and relatively massive. 3I Atlas, even at its closest approach, is nearly 700 times farther away than the Moon and perhaps 1 trillion times less massive. Even if we wildly overestimate 3I Atlas's mass, imagining it somehow 10 times larger and denser than observations suggest, the tidal effects on Earth would still be immeasurably small. You would have more tidal influence on Earth by jumping up and down in your backyard than 3I Atlas has at its closest approach. The orbital inclination adds another layer of safety and predictability. 3.1. Atlas approaches the solar system at a high angle relative to the plane where Earth and the other planets orbit. This retrograde high-inclination trajectory is actually typical for random interstellar objects, exactly what you'd expect from something that originated in a completely different stellar environment with no relationship to our solar system as formation. Could the Sun somehow capture it? This question reveals a fundamental misunderstanding of orbital energy. Capture requires removing exactly the right amount of kinetic energy at exactly the right moment. Natural capture is extraordinarily rare and requires very specific circumstances, usually involving multi-body gravitational interactions or atmospheric drag, neither of which applies to 3I Atlas. The escape energy dominates everything else. 3.1 Atlas carries enough kinetic energy relative to the Sun to escape the solar system, even if it started from rest at the Sun's surface. The planetary deflections it experiences are like trying to stop a freight train by throwing ping-pong balls at it, measurable in principle, irrelevant in practice. Unbody simulations, computer models that track the gravitational influences of all the planets simultaneously, confirm these analytical predictions. When you run 3I Atlas's trajectory forward or backward through time, accounting for every planetary perturbation, the result is consistent: hyperbolic approach, brief solar system passage, and hyperbolic departure. The historical context provides reassurance through familiarity. 1I ʻOumuamua followed a similar hyperbolic trajectory during its 2017 visit. 2I Borisov did the same in 2019 and 2020. The pattern is consistent. Interstellar objects visit, provide scientific opportunities, and depart without drama. But there's an important difference in public perception. Both previous interstellar visitors were discovered relatively late in their passages, when their trajectories were already well established and their departure was imminent. 3I Atlas was found earlier in its approach, providing more time for observations, but also more time for speculation and misunderstanding. The flotation with Mars, occasionally mentioned in early reports, deserves clarification. 3I Atlas's orbit does carry it through the general region of Mars's orbital distance, but Mars won't be anywhere near that location when the comet passes through. It's like saying two cars will collide because their travel paths cross on a map, even though they will be on those paths at different times. The timing is everything. Our ability to model and predict these celestial movements with such precision is one of the greatest triumphs of modern science. It allows us to separate genuine astronomical phenomena from the baseless myths and fears that can sometimes dominate public discussion. This is a scientific exploration, not a disaster movie, and the facts are far more interesting than the fiction. The fear-mongering and sensationalism often found in media and online platforms are not based on science, but on a lack of understanding. The physical impossibility of these scenarios provides a great opportunity to educate the public about the actual scale and dynamics of our solar system. The universe is a vast and mostly empty place, and the distances involved in these celestial passes are immense. The true danger lies not in distant harmless comets, but in a lack of scientific literacy and the propagation of misinformation. By patiently and clearly explaining the real science, we can replace fear with fascination and empower the public with knowledge. 3I Atlas is a guest, not a threat, and its visit is a precious gift of scientific data that will enrich our understanding of the cosmos for years to come. Mars orbiters, deep space missions, and solar observatories will continue monitoring its behavior. There is no concealment, no surprise capability, and no strategic positioning. There is just a comet following Newton's laws of motion with clockwork precision. The size mythology needs addressing, too. Early media reports occasionally conflate brightness with size, suggesting that 3I Atlas might be much larger than current estimates indicate. But brightness depends on surface area, reflectivity, and outgassing activity, not just size. A small, highly active comet can appear brighter than a large dormant one. Current observations constrain the nucleus to no more than about 5 to 6 kilometers across, and possibly much smaller. Even if 3I Atlas were larger than estimated, size alone doesn't create danger at these distances. A 10 kilometers comet at 270 million km is still utterly harmless to Earth. It's like worrying about getting wet from a water balloon thrown from the next state over. Let's establish an evidence standard for the rest of our investigation. Peer-reviewed papers carry the most weight, followed by preprints that are undergoing review, followed by conference presentations and press releases. Extraordinary claims require extraordinary evidence, and the more extraordinary the claim, the higher the evidence bar should be. NASA's official communications about 3I Atlas consistently emphasize its safe distance and predictable behavior. These are not bureaucratic cover-ups or attempts to prevent panic. They're accurate summaries of what the orbital mechanics actually show. When space agencies around the world agree on basic facts like trajectory and closest approach distance, those facts are extraordinarily reliable. The scientific community has developed sophisticated methods for detecting and characterizing potentially hazardous objects. The same surveys that found 3I Atlas routinely identify and track asteroids and comets that could pose genuine risks to Earth over timescales of centuries. These systems work. They're constantly improving, and they're operated by people whose careers depend on accuracy. Media literacy becomes crucial here. Headlines designed for clicks don't always reflect the content of the articles they introduce, and articles don't always accurately represent the scientific papers they discuss. The most reliable information comes directly from space agencies, major observatories, and the scientists actually conducting the observations. Visual effects in movies and television create unrealistic expectations about how space objects behave. Real comet tails are usually invisible to the naked eye, extend in directions determined by solar wind rather than orbital motion, and consist of materials so tenuous that it barely qualifies as matter at all. Real asteroid impacts require very specific size and velocity combinations to cause significant damage. Real orbital mechanics follow predictable mathematical rules that don't allow for dramatic last-minute course changes or surprise attacks. The myth-busting isn't meant to dismiss curiosity or discourage questions. Healthy skepticism and scientific inquiry go hand in hand, but they work best when directed toward understanding what's actually happening rather than imagining what might be happening if the laws of physics worked differently. Here's our promise for the rest of this investigation. We clearly distinguish between peer-reviewed results, preliminary findings, and speculative possibilities. We'll show our work when we make claims about distances, masses, and energies. We'll acknowledge uncertainty when it exists and avoid certainty when it doesn't. 3. Atlas offers plenty of genuine mysteries worth exploring. We don't need to invent fictional dangers to make it interesting. The truth about this interstellar visitor is remarkable enough without embellishment, and threatening enough to our preconceptions without being threatening to our planet. Mathematics doesn't lie. It doesn't exaggerate for dramatic effect, doesn't hedge its bets for political reasons, and doesn't care about our hopes or fears. When we apply the cold, precise language of orbital mechanics to 3I Atlas, the story it tells is both reassuring and illuminating. Let's start with the fundamentals of what makes an orbit hyperbolic. Every orbit has an eccentricity, a number that describes how stretched or circular the path is. Circles have an eccentricity of 0. Ellipses have eccentricities between 0 and 1. Parabolas have an eccentricity of exactly 1. And hyperbolas, the mathematical curves that describe escape trajectories, have eccentricities greater than 1. 3I Atlas has an eccentricity of approximately 6. This is not a measurement uncertainty or a preliminary estimate subject to revision. This is a fundamental characteristic determined by hundreds of precise position measurements from multiple observatories worldwide. An eccentricity of 6 means the object is moving far too fast to be captured by the sun's gravity. It came from interstellar space. It will return to interstellar space. And there's nothing in our solar system massive enough to change that fact. The velocity at infinity, the speed 3I Atlas would maintain if it were traveling through empty space far from any gravitational influences, is approximately 57 to 58 kilometers per second. This is its cosmic baseline speed. The velocity it carries is a relic of its formation and ejection from another star system. When combined with the sun's gravitational influence, this velocity determines every aspect of 3I Atlas's trajectory through our solar system. That inbound trajectory traces back to the constellation Sagittarius, not because 3I Atlas originated there recently, but because that's the direction it was traveling when it entered the sphere of the sun's gravitational influence. The actual journey from its birth star to our solar system likely took millions of years and involved a much more complex path through the galaxy. This gravitational landscape, here's where the mathematics becomes simultaneously elegant and reassuring. Once 3I Atlas entered our solar system, its entire future path became precisely predictable. Newton's laws of motion and gravity don't allow for surprises, course corrections, or dramatic last-minute changes. Every spacecraft navigation team in the world can calculate this trajectory to extraordinary precision using equations that have changed since the 17th century. Even if 3I Atlas were somehow equipped with rocket engines and guidance systems, which it emphatically is, not the energy required to alter its course enough to threaten Earth would be beyond anything humanity has ever built. Planetary deflections during the passage are real but minuscule. As 3I Atlas swings past the Sun, it will experience gravitational influences from Jupiter, Saturn, and the other planets. These influences will slightly modify its outbound trajectory, changing its direction by fractions of a degree and its speed by meters per second. But the fundamental character of the orbit remains unchanged. Hyperbolic in, hyperbolic out. The closest approach to Earth occurs in mid-December 2025 at approximately 1.6 to 1.8 astronomical units, roughly 270 million kilometers. At this distance, 3I Atlas exerts less gravitational force on Earth than Earth exerts on the International Space Station. The tidal effects are so negligible they fall below the threshold of measurement by our most sensitive instruments. To understand why, consider the mathematics of tidal forces. These forces depend not just on mass and distance, but on the gradient of gravitational field strength. The Moon creates noticeable tides on Earth because it's relatively close and relatively massive. 3I Atlas, even at its closest approach, is nearly 700 times farther away than the Moon and perhaps 1 trillion times less massive. Even if we wildly overestimate 3I Atlas's mass, imagining it somehow 10 times larger and denser than observations suggest, the tidal effects on Earth would still be immeasurably small. You would have more tidal influence on Earth by jumping up and down in your backyard than 3I Atlas has at its closest approach. The orbital inclination adds another layer of safety and predictability. 3.1. Atlas approaches the solar system at a high angle relative to the plane where Earth and the other planets orbit. This retrograde high-inclination trajectory is actually typical for random interstellar objects, exactly what you'd expect from something that originated in a completely different stellar environment with no relationship to our solar system as formation. Could the Sun somehow capture it? This question reveals a fundamental misunderstanding of orbital energy. Capture requires removing exactly the right amount of kinetic energy at exactly the right moment. Natural capture is extraordinarily rare and requires very specific circumstances, usually involving multi-body gravitational interactions or atmospheric drag, neither of which applies to 3I Atlas. The escape energy dominates everything else. 3I Atlas carries enough kinetic energy relative to the Sun to escape the solar system, even if it started from rest at the Sun's surface. The planetary deflections it experiences are like trying to stop a freight train by throwing ping-pong balls at it. Measurable in principle, irrelevant in practice. Unbody simulations, computer models that track the gravitational influences of all the planets simultaneously, confirm these analytical predictions. When you run 3I Atlas's trajectory forward or backward through time, accounting for every planetary perturbation, the result is consistent: hyperbolic approach, brief solar system passage, and hyperbolic departure. The historical context provides reassurance through familiarity. ʻOumuamua followed a similar hyperbolic trajectory during its 2017 visit. 2I. Borisov did the same in 2019 and 2020. The pattern is consistent. Interstellar objects visit, provide scientific opportunities, and depart without drama. But there's an important difference in public perception. Both previous interstellar visitors were discovered relatively late in their passages, when their trajectories were already well established and their departure was imminent. 3I Atlas was found earlier in its approach, providing more time for observations, but also more time for speculation and misunderstanding. The flotation with Mars, occasionally mentioned in early reports, deserves clarification. 3I Atlas's orbit does carry it through the general region of Mars's orbital distance, but Mars won't be anywhere near that location when the comet passes through. It's like saying two cars will collide because their travel paths cross on a map, even though they will be on those paths at different times. The timing is everything. Our ability to model and predict these celestial movements with such precision is one of the greatest triumphs of modern science. It allows us to separate genuine astronomical phenomena from the baseless myths and fears that can sometimes dominate public discussion. This is a scientific exploration, not a disaster movie, and the facts are far more interesting than the fiction. Picture an ancient iceberg, older than Earth itself, awakening after millions of years of deep freeze. As 3I Atlas draws closer to the Sun, something remarkable begins to happen. The sparse starlight that has warmed its surface for eons suddenly intensifies into the focused energy of our solar system's central furnace. This is the moment when a dark, frozen wanderer transforms into an active comet. The physics are elegantly simple. Sunlight carries energy, and that energy heats whatever it touches. As 3I Atlas approaches perihelion, solar heating penetrates its surface layers, causing frozen materials to sublimate, transforming directly from ice to vapor without passing through a liquid phase. This outgassing process creates the characteristic coma, the extended atmosphere of gas and dust that makes comets visible across vast distances. But 3I Atlas isn't following the typical script. Most comets in our solar system are dominated by water ice. When they approach the Sun, water sublimation creates the bulk of their coma and tail. Carbon dioxide, carbon monoxide, and other compounds contribute, but water usually takes the lead role in the outgassing drama. The James Webb Space Telescope (JWST) revealed something different. 3I Atlas shows unusually strong carbon dioxide emissions compared to water, with early estimates suggesting a ratio approaching 8:1. This isn't just unusual, it's a complete inversion of what we normally see. The SPHEREX mission added another piece to the puzzle. Its wide-field spectral observations mapped the carbon dioxide coma extending for hundreds of thousands of kilometers, nearly the distance from Earth to the Moon. Meanwhile, water and carbon monoxide emissions that should announce themselves clearly in this spectral range were conspicuously absent. These are preliminary results, the kind that make scientists excited and nervous simultaneously. The teams analyzing this data are still refining their measurements, still double-checking their instruments, still making sure they're not seeing instrumental artifacts or calibration errors. But if these observations hold up under scrutiny, they're pointing towards something genuinely extraordinary. The carbon dioxide dominance suggests several possibilities, each with intriguing implications. Perhaps 3I Atlas formed in the outer reaches of its birth system, beyond the carbon dioxide ice line where carbon dioxide freezes before water does. This would place its origin in a region analogous to our outer asteroid belt or beyond, in the cold, dark zones where only the most volatile materials remain gaseous. Alternatively, 3I Atlas might have developed a surface crust that acts like a selective valve, allowing carbon dioxide to escape while trapping water beneath. Think of it as cosmic permafrost, an outer layer that insulates the interior and controls which materials can sublimate under solar heating. Both scenarios challenge our standard models of how outer protoplanetary disks distribute their chemical inventory. We're not just looking at one oddball comet, we're potentially glimpsing an entirely different approach to volatile chemistry and planetary formation. The dust production mechanics become particularly interesting when carbon dioxide leads the outgassing process. Water vapor has specific properties when it comes to lifting and accelerating dust particles away from a comet's nucleus. Carbon dioxide behaves differently, with different expansion rates, different cooling properties, and different abilities to entrain solid particles. This means the tail morphology and brightness evolution of 3I Atlas might not follow familiar patterns. The dust distribution might be different. The particle size ranges might be unusual. The overall appearance in telescopic images might challenge expectations based on water-dominated comets. Visibility expectations need to be managed carefully here. Despite its chemical activity, 3I Atlas won't necessarily put on a spectacular show for casual observers. The geometry of its passage places it behind the sun's glare during peak activity, making Earth-based observations challenging precisely when the comet is most active. This timing creates a natural experiment in comparative comet science. We can observe 3I Atlas during its approach, lose sight of it during solar conjunction, then pick up observations again as it recedes from the sun. The before and after comparison will reveal how perihelion passage affects its composition, outgassing rates, and dust production. Spacecraft positioned throughout the solar system fill the observation gap during solar conjunction. Mars orbiters can watch the comet's behavior when Earth-based telescopes are blinded by solar glare. This multi-platform approach provides unprecedented coverage of a comet's complete passage through the inner solar system. The comparison with typical solar system comets illuminates just how unusual 3I Atlas appears to be. Most comets show water emission lines dominating their spectra near 1 astronomical unit from the Sun. They produce predictable ratios of different molecular species. They follow well-understood patterns of brightness, variation, and tail development. 3I Atlas seems to be writing its own rules. The grain size analysis from ongoing studies will reveal whether carbon dioxide-dominated outgassing produces different dust characteristics than water-dominated systems. Larger grains, smaller grains, different mineral compositions, unusual shapes. All of these factors could distinguish interstellar dust from solar system dust in ways we are only beginning to understand. Gas velocity measurements add another layer of complexity. Different molecular species sublimate at different rates and expand away from the nucleus at different speeds. Carbon dioxide has different thermodynamic properties than water, which could create different pressure gradients, different expansion patterns, and different interactions with the solar wind. Fragmentation likelihood becomes a relevant concern as solar heating intensifies. Some comets break apart under thermal stress, especially if they have weak internal structure or contain materials with different expansion coefficients. 3I Atlas's unusual composition might make it more or less susceptible to fragmentation, a question that can only be answered through careful monitoring. The multiple apparitions across the solar conjunction gap will provide crucial data about its temporal evolution. How does the comet's behavior change as it approaches perihelion? How does it respond to peak solar heating? How does its activity decline as it recedes toward interstellar space? The tri-panel imaging from JWST offers a template for understanding molecular distribution. Total flux shows the overall activity level. The 4.3 micrometer channel highlights carbon dioxide emission. The 2.7 micrometer channel reveals water emission. The contrast between these channels tells the story of 3I Atlas's unusual chemistry. For public outreach, the carbon dioxide coat analogy helps explain why some comets behave differently than others. Just as different planets have different atmospheric compositions, different comets carry different chemical signatures that reflect their formation environments and evolutionary histories. The caveat about compositional ratios bears repeating. These measurements will be refined as peer review proceeds and analysis techniques improve. What we're seeing now represents the first draft of 3I Atlas's chemical story, not the final version, but even as preliminary results. These observations are reshaping our understanding of volatile chemistry and planetary formation. They suggest that the processes that build worlds around other stars can produce outcomes very different from our solar system's template. They hint that interstellar space might be populated by a diverse collection of chemical signatures, each telling a unique story about planetary formation under different conditions. The awakening of 3I Atlas under our sun's influence isn't just about one comet's behavior. It's about the diversity of outcomes possible when gravity, chemistry, and time collaborate to build worlds around stars throughout the galaxy. The romantic notion of launching a spacecraft to rendezvous with 3I Atlas captures our imagination, racing across the solar system to shake hands with a visitor from another star. Unfortunately, the mathematics of orbital mechanics and spacecraft engineering are less romantic than our ambitions. The brutal constraints are straightforward. 3I Atlas is moving at 57 kilometers per second relative to the Sun. It was discovered late in its approach. The mathematics of orbital mechanics and spacecraft engineering are less romantic than our ambitions. The brutal constraints are straightforward. 3I Atlas is moving at 57 kilometers per second relative to the Sun. It was discovered in July 2025, giving us roughly 3 to 4 months before its perihelion passage. Even our fastest spacecraft take years to reach the outer solar system, and that's when we can plan trajectories carefully and launch at optimal times. Building and launching a dedicated intercept mission would require capabilities that exist only in science fiction. We would need a spacecraft that could accelerate to unprecedented velocities, survive the intense radiation environment near the Sun, and somehow match course with an object moving faster than anything we've ever attempted to intercept. But here's the beautiful thing about modern space exploration. We don't need to build new missions to conduct extraordinary science. We just need to be clever about using the assets we already have positioned throughout the solar system. The geometry of 2025 creates some remarkable opportunities. Several major spacecraft find themselves in advantageous positions during 3I Atlas's passage, not through careful planning, but through the fortunate alignment of mission timelines and orbital mechanics. The European Space Agency CSA JUICE mission, the Jupiter Icy Moons Explorer, completed its Venus gravity assist on August 31, 2025, placing it in an excellent position for 3I Atlas observations. At approximately 68 million km from the comet during key observation windows, JUICE carries sophisticated cameras and spectrometers that could provide unprecedented close-up views of an interstellar visitor. NASA's Psyche spacecraft, currently en route to study a metallic asteroid, sits roughly 45 million km from 3I Atlas during its passage. While Psyche's instruments are optimized for asteroid science rather than comet observations, they could still capture valuable data about the comet's activity and dust environment. Perhaps most intriguingly, the Mars Orbiter constellation finds itself perfectly positioned for 3I Atlas observations. NASA's Mars Reconnaissance Orbiter, China's Tianwen-1 mission, and the UAE's Hope Orbiter all enjoy front-row seats at distances of just 29 million kilometers from the comet. These aren't purpose-built comet missions. They are existing spacecraft with their own primary objectives, carefully planned observation schedules, and scientific priorities. But the fortunate alignment of orbits creates opportunities for multi-platform observations that would have been impossible to plan deliberately. The advantages of spacecraft observations become crucial around perihelion when Earth's view of 3I Atlas becomes severely compromised by solar glare. Ground-based telescopes lose their target behind the Sun's overwhelming brightness precisely when the comet is most active and most scientifically interesting. Spacecraft positions throughout the solar system don't face this limitation. They can maintain clear lines of sight to 3I Atlas throughout its passage, watching the tail develop, monitoring outgassing behavior, and potentially sampling dust particles if orbital mechanics align favorably. The measurement possibilities depend on each spacecraft's instrument complement. Imaging systems can track morphological changes in the coma and tail. Spectrometers can analyze the chemical composition of outgassing materials. Dust detectors can characterize particle sizes and impact rates. If the spacecraft happens to pass through extended dust environments, these observations aren't guaranteed, they're opportunistic. Spacecraft instruments aren't necessarily optimized for comet science, and primary mission requirements always take priority. Mission planners must balance the scientific value of 3I Atlas observations against the needs of the primary mission objectives. But even modest resolution imaging and basic spectroscopy from these platforms could provide invaluable data about how an interstellar comet behaves when it's impossible to observe from Earth. The heliophysics community offers additional observational platforms. The Solar and Heliospheric Observatory, the Parker Solar Probe, and the upcoming Punch mission all maintain specialized instruments designed to study the solar wind and space weather environment. These spacecraft could observe 3I Atlas's interaction with solar particles and magnetic fields, providing insights into how interstellar material responds to our sun's influence. Risk management becomes a crucial consideration for any spacecraft observations. Direct fly-throughs of comet tails, while scientifically valuable, expose spacecraft to potential damage from high-velocity dust impacts. Mission planners must weigh scientific opportunity against hardware protection, especially for spacecraft with ongoing primary missions worth hundreds of millions of dollars. Passive sensing from safe distances offers the optimal balance of scientific value and operational safety. Spacecraft can observe 3I Atlas from thousands or tens of thousands of kilometers away, well outside any dust hazard zones, while still collecting scientifically valuable data. The data choreography requires careful coordination across multiple space agencies and mission teams, timing observations to complement each other, sharing data rapidly for cross-validation, and coordinating instrument settings for maximum scientific return. All of these factors require diplomatic finesse and technical precision. Before and after comparisons become particularly valuable when combining Earth-based observations with spacecraft data. Ground telescopes can characterize 3I Atlas during its approach. Spacecraft fill the observation gap during solar conjunction. Ground telescopes resume monitoring as the comet emerges from behind the sun's glare. This coordinated approach provides unprecedented coverage of a comet's complete passage through the inner solar system, revealing how perihelion passage affects composition, activity levels, and dust production in ways that single-platform observations cannot match. Citizen engagement remains possible even without dedicated spacecraft missions. Public webcasts of observing sessions, real-time data sharing from professional observations, and citizen science projects for image processing and data analysis allow the public to participate directly in cutting-edge research. Ground-based facilities like the Gemini Observatory in Lab have demonstrated the public appetite for live observing sessions during previous interstellar visitor passages. These events combine education with entertainment, allowing people worldwide to watch professional astronomers conduct real research in real time. The bottom line is both disappointing and encouraging. We can't launch a Hollywood-style intercept mission to 3I Atlas. The physics and timing simply don't work. But the clever coordination of existing spacecraft and ground-based facilities can provide scientifically rich observations that might be even more valuable than a single dedicated mission. This approach represents the future of space science in an era of routine interstellar visitors. Instead of building expensive bespoke missions for each target, we maintain a constellation of capable spacecraft and ground-based facilities that can rapidly pivot to study unexpected opportunities. 3I Atlas is testing this coordinated approach in real time, demonstrating whether distributed observation networks can match the scientific return of traditional flagship missions while maintaining the flexibility to respond to targets discovered with little advanced warning. The results will inform how we prepare for the next interstellar visitor and the one after that, as these cosmic travelers transition from rare curiosities to routine scientific opportunities. Every piece of cosmic debris tells a story about where it came from, but 3I Atlas might be carrying one of the oldest stories ever delivered to our scientific instruments. The preliminary evidence suggests we're looking at material that predates Earth's formation, a geological sample from the galaxy's youth, when the universe was fundamentally different than it is today. The kinematic evidence is tantalizing but still under debate. Several analyses of 3I Atlas's motion through space suggest it originated in the Milky Way's thick disk, a population of older metal-poor stars that formed during the galaxy's early history. If this interpretation holds up, we're examining material that's at least 7 billion years old, possibly much older. To understand why this matters, we need to think about how the galaxy builds itself over cosmic time. Stars form in waves, with different generations using different raw materials and following different patterns of chemical evolution. The thick disk represents stars that formed during cosmic noon, the peak era of star formation when the universe was roughly half its current age and galaxies were busy assembling themselves from smaller components. But the kinematic story isn't settled. A competing analysis using data from the Gaia Space Telescope suggests 3I Atlas might have originated in the thin disk, a younger population of stars with near-solar metallicity, implying a more recent origin in a star system much like our own. This disagreement isn't a failure of science, it's science working as designed. Different teams using different analysis techniques and different datasets are testing each other's results, refining measurements, and gradually converging on the truth. The process takes time, but it produces reliable answers. The chemical composition adds crucial evidence to this cosmic detective story. The carbon dioxide-rich nature of 3I Atlas points toward formation beyond the carbon dioxide ice line in its parent star system, or under specific irradiation conditions that favor carbon dioxide retention over water ice preservation. These chemical signatures are like fingerprints from exoplanetary nurseries. We'll never visit directly. When planetary systems form, they scatter leftover planetesimals, chunks of rock, metal, and ice throughout interstellar space. These ejected building blocks carry chemical signatures that sample the materials available in their birth environments. The exoplanet connection deserves emphasis. Every interstellar comet represents a piece of a failed planet, a chunk of material that almost became part of a world, but was instead ejected during the chaotic early phases of planetary system formation. By studying these cosmic refugees, we're essentially conducting archaeology on exoplanetary formation processes. If 3I Atlas truly originated in the thick disk, the implications are staggering. We would be examining material that formed when the galaxy was younger, when heavy elements were less common, and when the chemical inventory available for planet formation was significantly different from what we see today. This connects to fundamental questions about planetary formation across cosmic time. Did early planetary systems form differently because they had access to different materials? Were volatiles like water and carbon dioxide distributed differently in primordial disks? How has the efficiency of planet formation changed as the galaxy has evolved? The comparative interstellar object science is building a catalog of these chemical signatures, allowing us to compare the building blocks of our own solar system to those from other stars. 1I ʻOumuamua was a mystery, likely an asteroid from a system that formed differently. 2I Borisov was a normal comet, suggesting its parent system's chemistry was similar to ours. 3I Atlas is a weird comet, offering a third data point that shows the diversity of outcomes. Together, these three objects are painting a picture of a galactic neighborhood full of different kinds of planetary systems, each with its own unique history and chemistry. The ultimate goal is not just to find more interstellar objects, but to use them as probes to understand how the galaxy builds planets from scratch. 3I Atlas is an invaluable piece of this puzzle, teaching us about the diversity of planetary formation and the ancient history of our galactic home. The small sample of interstellar objects we've detected already shows a diversity that challenges our assumptions about our own solar system. 2I Borisov appeared water-rich and relatively normal. 1I ʻOumuamua was so unusual that astronomers still debate whether it was a comet at all. 3I Atlas seems carbon dioxide-dominated and chemically distinct. This small sample suggests that interstellar space contains a variety of chemical signatures, each reflecting different formation environments and evolutionary pathways. As our detection capabilities improve and more interstellar visitors are discovered, we're building a census of how planetary formation processes vary across different stellar environments. The discovery rate projections are encouraging. The upcoming Vera C. Rubin Observatory is expected to find interstellar objects at a rate ranging from roughly 1 per year to potentially dozens per year, depending on their actual population density and size distribution. This transition from rare curiosities to routine discoveries will revolutionize interstellar object science. With larger sample sizes, astronomers will be able to perform population studies, looking for correlations between chemical composition and kinematics, between size and activity level, and between orbital characteristics and formation environment. Individual objects like 3I Atlas provide fascinating case studies, but population statistics reveal the underlying physical processes. The thick disk hypothesis, if confirmed, opens a window into cosmic history that is otherwise inaccessible. We can study the oldest stars in our galaxy, but their surfaces don't preserve information about the conditions in which they formed billions of years ago. Comets like 3I Atlas might retain that chemical memory in their frozen interiors. This connects to broader questions about cosmic evolution. When did the first planetary systems form? How different were they from modern systems? What role did early planet formation play in the chemical evolution of the galaxy? These questions require data from the earliest epochs of galactic history, and 3I Atlas might be providing exactly that. The preprint culture in astronomy means we can follow these debates in real time as they develop. Papers appear on arXiv before peer review, allowing the community to see preliminary results and begin responding with additional observations or alternative interpretations. This transparent process shows how scientific consensus develops gradually through competition between different ideas. But we need to be careful about preliminary results. The thick disk versus thin disk debate will likely continue for months or years as additional kinematic analyses are completed and chemical composition measurements are refined. Science communication requires clearly distinguishing between provisional findings and established results. The galaxy mapping context helps visualize what we're discussing. The Milky Way structure includes several distinct components: a thin disk of young stars like the Sun, a thick disk of older stars formed during the galaxy's early assembly, a central bulge of ancient stars, and a spherical halo of the galaxy's oldest stellar populations. Each component represents a different era in galactic evolution with different chemical compositions, different kinematics, and different histories of star and planet formation. If 3I Atlas originated in the thick disk, it is carrying information from an era when the galaxy was still actively growing through mergers with smaller galaxies. The confidence metrics that accompany these analyses deserve attention. Kinematic studies typically provide error bars and statistical significance measures that indicate how reliable the conclusions are. Understanding these uncertainties is crucial for evaluating competing claims about 3I Atlas's origin. The ultimate payoff extends beyond one comet's biography. If we can reliably determine the galactic origins of interstellar objects, we gain a new tool for studying galactic evolution, stellar populations, and the history of planet formation across cosmic time. 3I Atlas might be more than just a visitor from another star system. It might be a messenger from another era entirely, carrying news from the galaxy's youth about how worlds were built when the universe was fundamentally different than it is today. The question isn't just where 3I Atlas came from, but when, and what that timing reveals about the long history of planets, stars, and galaxies building themselves from cosmic dust. The discovery of 3I Atlas represents more than just another entry in the catalog of interstellar visitors. It's a stress test of our scientific infrastructure, a validation of our survey capabilities, and a preview of how astronomy will function in the coming decade when such visitors transition from rare curiosities to routine discoveries. The survey upgrade pathway is already clear. The Vera C. Rubin Observatory, scheduled to begin operations in the mid-2020s, will revolutionize our ability to detect and characterize interstellar objects. Current estimates suggest Rubin could find anywhere from one interstellar visitor per year to potentially dozens annually, depending on the actual population density and size distribution of these objects in interstellar space. This dramatic increase in the discovery rate will transform interstellar object science from a field driven by individual case studies to one capable of population statistics and comparative analysis. Instead of examining each visitor as a unique specimen, we'll begin to see patterns, correlations, and systematic differences that reveal underlying physical processes. The pipeline maturity improvements are already visible. ATLAS, the Catalina Sky Survey, and LINEAR have refined their algorithms for detecting objects with unusual motion characteristics. The rapid identification of 3I Atlas as potentially interstellar demonstrates how these systems have learned from previous discoveries like 1I ʻOumuamua and 2I Borisov. Future interstellar visitors will be flagged more quickly, characterized more efficiently, and studied more comprehensively than their predecessors. The learning curve from 3I Atlas will benefit every subsequent discovery, creating a cumulative improvement in our response capabilities. The planetary defense literacy angle deserves particular attention. 3I Atlas provides a perfect teaching moment about uncertainty, measurement precision, and the difference between unknown and dangerous. The object's safe distance and predictable trajectory demonstrate how astronomical calculations work and why they're reliable. This educational opportunity matters because planetary defense depends on public understanding and support. When genuinely hazardous objects are discovered in the future, the public's response will be shaped by their familiarity with how these calculations work and why. Scientists can make confident predictions about trajectories and impact risks. Mission planning philosophies are evolving in response to discoveries like 3I Atlas. The Comet Interceptor mission represents a new approach. Instead of launching toward a specific target, position a spacecraft at a gravitationally stable Lagrange point and wait for interesting targets to announce themselves. This wait-and-pounce strategy could become the standard for studying unpredictable targets with short discovery lead times. The career and training implications ripple through the astronomical community. Graduate students and postdocs are gaining experience with rapid response observational campaigns, multi-facility coordination, and international collaboration under time pressure. These skills will be increasingly valuable as transient astronomy becomes more common across multiple subfields. 3.1. Atlas mobilizes research teams across dozens of institutions and facilities. Students learn to work with data from JWST, Hubble, spherics, and ground-based telescopes simultaneously. They practice coordinating observations across time zones and organizational boundaries. They develop expertise in moving target tracking, spectroscopic analysis, and multi-wavelength data fusion. These experiences produce researchers who are comfortable with complexity, uncertainty, and collaboration, exactly the skills needed for 21st century astronomy. The public engagement spillover effects extend far beyond astronomy. Live telescope sessions, citizen science projects, and educational programs around 3I Atlas introduce people to scientific methodology, international cooperation, and the excitement of discovery. These experiences influence career choices, voting patterns, and public support for scientific research. Educational institutions are incorporating 3I Atlas into lesson plans about orbital mechanics, spectroscopy, and scientific methodology. Students learn to distinguish between preliminary results and peer-reviewed findings, between speculation and evidence-based conclusions, and between media hype and scientific reality. The budget implications deserve realistic assessment. The scientific windfall from 3I Atlas doesn't require massive new expenditures or congressional appropriations. It primarily represents coordination and scheduling among existing facilities and missions. The most expensive component might be the additional staff time needed for data analysis and paper preparation. This efficiency demonstrates the value of maintaining a diverse, capable scientific infrastructure. Instead of building specialized missions for each target of opportunity, we maintain a portfolio of capabilities that can rapidly pivot to study unexpected discoveries. The return on investment is extraordinary. The next decade roadmap is becoming clear. Improved surveys will detect interstellar objects earlier and more reliably. Better alert systems will notify the global community more quickly. Enhanced coordination protocols will maximize scientific return from limited observing opportunities. Eventually, interceptor missions positioned at strategic locations will provide close-up studies of the most interesting visitors. Each step builds on lessons learned from current discoveries. 3I Atlas provides crucial experience with the entire pipeline, from detection to detailed characterization to scientific interpretation. The metric to track is response time, how quickly the community can move from discovery to initial characterization to detailed follow-up observations. 3.1 Atlas establishes a baseline for this metric that future discoveries should improve upon. Rapid response requires not just better instruments but better coordination, data sharing agreements, observing time allocation procedures, and international cooperation frameworks all need refinement. Based on real-world experience with objects like 3I Atlas, the infrastructure investments are largely invisible to the public but crucial for scientific success. Better computational resources for orbit determination, improved communication systems for coordinating observations, and enhanced data archiving for long-term studies. These behind-the-scenes improvements determine whether discoveries like 3.1 Atlas become transformative science or missed opportunities. The competence development aspect deserves emphasis. The real outcome for humanity isn't dramatic sky shows or existential threats. It's the gradual development of systematic capabilities for understanding our cosmic environment. We're becoming better at detecting unexpected visitors, characterizing their properties, predicting their behavior, and learning from their compositions. This competence extends beyond interstellar visitors to potentially hazardous asteroids, solar system exploration, and space situational awareness. The techniques developed for 3I Atlas improve our ability to track and understand any small body moving through space. The international collaboration templates being established now will serve as models for future discoveries. When the next interstellar visitor arrives, or when a genuinely hazardous asteroid is discovered, the coordination mechanisms tested on 3I Atlas will provide proven frameworks for a rapid and effective response. Perhaps most importantly, 3I Atlas normalizes the idea that our solar system exists within a larger galactic community. These visitors remind us that planetary formation occurs throughout the galaxy, that other star systems occasionally share their leftovers with us, and that our cosmic neighborhood is more dynamic and interconnected than previous generations realized. This shift in perspective, from cosmic isolation to galactic citizenship, may ultimately be 3I Atlas's most significant contribution to human understanding. We're not alone in space, not in the science fiction sense of alien civilizations, but in the deepest sense of participating in galaxy-wide processes of planetary formation and evolution. The systems we're building to study 3I Atlas prepare us for a future where such discoveries are routine, where interstellar archaeology becomes a standard astronomical discipline, and where humanity's understanding of planetary formation extends far beyond our own solar system's example. Now we enter the realm of speculation, the territory where science fiction meets scientific methodology. Some researchers, blogs, and preprint servers have suggested that 3I Atlas might not be a natural comet at all. Could it be artificial? Could it represent technology from another civilization? Could it pose risks beyond simple gravitational mechanics? Let's examine these claims with the same rigorous skepticism we apply to any extraordinary assertion. The artifact hypothesis requires extraordinary evidence because it makes extraordinary claims. If 3I Atlas were artificial, constructed or modified by intelligent beings, it would represent the most significant discovery in human history. The implications would reshape our understanding not just of our cosmic environment, but of our place in the universe itself. So what evidence would convince scientists that 3I Atlas is artificial rather than natural? The checklist is demanding but clear. Non-gravitational accelerations that are inconsistent with normal outgassing would be a strong indicator. Natural comets experience slight course corrections as sublimating gases create rocket-like thrust. But these accelerations follow predictable patterns based on solar, heating, and rotation. Artificial objects might show accelerations that don't match these patterns. Engineered reflectance characteristics would provide another crucial signature. Natural comet surfaces are chaotic mixtures of ice, rock, and organic compounds with irregular shapes and random orientations. Artificial surfaces might show geometric patterns, unusual brightness variations, or reflectance spectra that don't match any known natural materials. Coherent radio emissions would be perhaps the most definitive evidence. Natural comets don't generate organized radio signals beyond thermal noise and occasional plasma interactions. Artificial objects, especially those designed for communication or navigation, might broadcast structured signals that stand out clearly against the cosmic background. Controlled maneuvers would provide unambiguous proof of artificial origin. Natural objects follow predictable trajectories determined by gravity and outgassing forces. Artificial objects might demonstrate course corrections, orbital adjustments, or trajectory changes that couldn't be explained by known physical processes. The current observational evidence for 3I Atlas shows none of these artificial signatures. JWST observations reveal classical molecular emission lines from carbon dioxide consistent with normal cometary output. The Hubble Space Telescope shows a typical teardrop-shaped dust coma that matches theoretical predictions for natural comets under solar heating. Spherix mapping reveals extended carbon dioxide envelopes that follow expected patterns for gas expansion in the vacuum of space. Radio telescopes have monitored 3I Atlas for any unusual emissions. The searchers have revealed thermal radiation consistent with a cold object warming under solar heating, but no structured signals, no coherent transmissions, and no evidence of artificial radioactivity. Astrometric measurements, the precise tracking of the object's position over time, show trajectory changes consistent with natural outgassing forces. The slight accelerations observed match theoretical predictions for carbon dioxide sublimation from a rotating nucleus. There's no evidence of controlled maneuvers or artificial course corrections. The media literacy component becomes crucial when evaluating artifact claims. Provocative blog posts and speculative articles spread faster through social media than careful scientific analysis. The attention-grabbing headline, "Could interstellar visitor be alien probe?" generates more clicks than spectroscopic analysis confirms natural comet composition. This isn't a conspiracy or cover-up. It's the natural consequence of how information spreads in the internet age. Sensational possibilities travel faster than mundane realities, regardless of their scientific merit. The dark forest hypothesis, popularized by science fiction author Liu Cixin, suggests that hostile civilizations might send artificial objects to scout or attack other worlds. This makes for compelling storytelling, but it requires evidence far beyond the realm of current observations. Science fiction scenarios are worth considering as thought experiments, but they belong in the entertainment category until evidence elevates them to scientific hypothesis. There's nothing wrong with speculation as long as it's clearly labeled as such and doesn't masquerade as established fact. How would the scientific community test an artificial origin hypothesis if evidence emerged? The protocols are already in place. Radio SETI organizations maintain arrays specifically designed to detect artificial signals. Radar installations can probe objects for unusual structural characteristics. Precise astrometry can detect controlled maneuvers that violate natural orbital mechanics. The thresholds for changing scientific consensus about 3I Atlas are high but achievable. A single unexplained radio signal might trigger additional observations, but wouldn't constitute proof. Multiple independent detections of structured transmissions confirmed by different facilities using different techniques would be much more convincing. Similarly, one anomalous trajectory measurement might indicate instrumental error or unknown outgassing behavior. A pattern of controlled maneuvers observed by multiple tracking stations over extended periods would be much harder to explain through natural processes. The evidence ladder provides a framework for evaluating extraordinary claims. Rumors and speculation occupy the bottom rung. Preprint papers that haven't undergone peer review represent preliminary findings that might or might not survive scrutiny. Peer-reviewed papers that have survived expert examination carry much more weight. Scientific consensus emerges when multiple independent research groups reach similar conclusions using different methods. 3.1 Atlas artifact claims currently occupy the bottom rungs of this ladder. They represent speculation and preliminary suggestions rather than established scientific findings. The ʻOumuamua case study provides historical context for how these debates evolve. When 1I ʻOumuamua was discovered in 2017, its unusual elongated shape and slight non-gravitational acceleration prompted speculation about an artificial origin. Some researchers suggested it might be a solar sail or a probe from another civilization. Over time, additional observations and theoretical work provided natural explanations for ʻOumuamua's unusual characteristics. The current scientific consensus favors a natural origin, though some uncertainty remains about the specific mechanisms responsible for its behavior. This pattern, initial speculation followed by a gradual convergence toward natural explanations, reflects how science processes extraordinary claims. The system is designed to be skeptical of dramatic assertions, while remaining open to genuine evidence when it appears. The guardrail against ridicule deserves emphasis. Curiosity about artificial origins isn't inherently unscientific. CTI research, technosignature studies, and searches for evidence of technological civilizations represent legitimate scientific disciplines. The key is channeling curiosity into testable predictions rather than unfounded assertions. Good science distinguishes between "we do want to have evidence for this" and "this is impossible." The absence of evidence for an artificial origin doesn't prove 3I Atlas is natural. It just means the artifact hypothesis lacks supporting data. If compelling evidence of an artificial origin did emerge and be clear, current observations strongly suggest it won't. The implications would be epical, and would alter human civilization's understanding of its cosmic context. The discovery protocols for such a scenario already exist. The International Academy of Astronautics maintains guidelines for announcing potential extraterrestrial contact. The scientific community has procedures for verification, confirmation, and public communication of extraordinary discoveries, but extraordinary claims require extraordinary evidence, and that evidence simply doesn't exist for 3I Atlas. Every observation to date supports a natural comet origin. The chemical signatures, physical behavior, and trajectory characteristics all match theoretical predictions for interstellar comets. The outcome framing helps maintain perspective. If artifact evidence somehow emerged, which current data strongly argues against, it would indeed be the most significant discovery in human history. Absent such evidence, 3I Atlas remains a scientifically treasured comet that's expanding our understanding of planetary formation processes across the galaxy. The speculation serves a useful purpose by highlighting the importance of evidence-based reasoning and the scientific method. By examining what evidence would be required to support an artifact hypothesis, we learn to recognize the difference between genuine scientific inquiry and baseless fantasy. The artifact hypothesis reminds us that the universe is full of possibilities we haven't yet discovered. But it also reminds us that distinguishing between possibilities and actualities requires careful observation, rigorous analysis, and healthy skepticism about claims that seem too extraordinary to be true. 3I Atlas offers plenty of genuine mysteries worth exploring without invoking artificial origins. Its unusual chemical composition, ancient age, and interstellar journey provide more than enough scientific interest to justify careful study. In the age of social media and conspiracy theories, every unusual celestial event becomes a canvas for elaborate speculation. 3I Atlas, with its mysterious origin and unusual composition, has attracted its share of creative interpretations. Let's examine some of the more persistent claims and see how they hold up against actual evidence. The radio signals from the comet narrative represents perhaps the most common type of misinterpretation. Several social media posts have claimed that 3I Atlas is broadcasting structured radio transmissions, potentially indicating artificial intelligence or alien communication attempts. The reality is more mundane but also more interesting from a scientific perspective. Radio telescopes have indeed observed 3I Atlas, but they detect only thermal radiation, the natural radio emissions that any cold object produces when warmed by solar heating. These emissions follow predictable patterns based on the object's temperature, composition, and rotation rate. The sensitivity limits of current radio observations are well understood. If 3I Atlas were broadcasting at the power levels typical of human technology, our radio telescopes would easily detect such signals. The absence of structured emissions doesn't prove that artificial signals are impossible. It demonstrates that none exist at detectable power levels. Thermal noise considerations matter here. Space is filled with natural radio emissions from stars, galaxies, and cosmic ray interactions. Any artificial signal would need to stand out clearly against this background radiation. Pattern recognition algorithms, specifically designed to identify structured signals, have found nothing unusual in 3I Atlas observations. Beam shape analysis adds another layer of technical sophistication to radio searches. Natural thermal emissions spread equally in all directions, while artificial transmissions often show directional preferences. The radio emissions from 3I Atlas show the isotropic characteristics expected from natural thermal radiation. The geometric paths and numerology category of claims deserves special attention because it sounds almost scientific. Some online discussions have suggested that 3I Atlas's orbital parameters contain hidden mathematical relationships or deliberately chosen geometric patterns that indicate intelligent design. These claims misunderstand how orbital mechanics actually works. 3I Atlas's trajectory results from gravitational interactions with the Sun and planets. Following Newton's laws of motion with exacting precision, the orbital elements' eccentricity, inclination, and perihelion distance are determined by the object's velocity and position when it entered the solar system, not by any conscious design process. Hyperbolic orbits for interstellar objects are mathematically inevitable given their high velocities relative to the Sun. The specific parameters of 3I Atlas's orbit result from the random direction and speed it carried from its parent star system, modified by billions of years of galactic dynamics. The time to hide at perihelion conspiracy theory misrepresents the geometry of solar system observations. 3I Atlas isn't hiding behind the Sun. It's following a predictable trajectory that happens to place it in solar conjunction during late October 2025. This timing is determined by orbital mechanics, not strategic planning. The comet's approach trajectory and Earth's orbital position combine to create the observation geometry. Spacecraft positioned throughout the solar system will maintain clear views of 3I Atlas during the conjunction period, providing continuous monitoring capabilities. Solar conjunction is a common occurrence for objects orbiting the Sun. Mars experiences superior conjunction approximately every 26 months. Venus goes through conjunction phases regularly. These geometric alignments are natural consequences of orbital motion, not evidence of concealment attempts. The reproducible verification methods are crucial for evaluating these claims. Anyone can track updates on NASA's official 3I Atlas webpage, which provides regular updates on orbital parameters, observation schedules, and scientific results. ESA maintains similar resources for JWST observations and European spacecraft monitoring. Date stamps and version tracking allow interested parties to see how measurements evolve as more observations become available. Initial orbital estimates get refined as the observation arc lengthens. Preliminary composition measurements get updated as spectroscopic analysis improves. This transparent process demonstrates how scientific knowledge develops through accumulated evidence. Open data policies ensure that interested researchers worldwide can access the raw observations. Hubble Space Telescope images become publicly available through the Space Telescope Science Institute archives. NOILAB press releases include both processed images and technical details about observation methods. JWST spectra and analysis results are shared through the Space Telescope European Coordinating Facility. The claim versus check methodology provides a template for evaluating extraordinary assertions. When someone claims that 3I Atlas shows unusual behavior, interested parties can check current NASA updates, compare with official orbital predictions, and verify whether observations match the claims. URL verification helps distinguish between reliable sources and speculative websites. NASA, ESA, and major observatories maintain official domains with consistent formatting and citation practices. These sources provide technical details, error bars, and acknowledgments of uncertainty where appropriate. Scientific uncertainty requires careful communication. Preprints posted to arXiv represent preliminary research that hasn't undergone peer review. These papers can contain valuable insights, but may also include errors or interpretations that don't survive expert scrutiny. The arXiv identifier system allows tracking of paper versions and subsequent publications in peer-reviewed journals. The peer review process serves as quality control for scientific claims. Papers accepted by journals like Astronomy and Astrophysics, the Astrophysical Journal, or Nature have survived expert examination by researchers familiar with the relevant analysis, techniques, and observational methods. Reading spectroscopic data requires some technical background but follows consistent principles. The 4.3 micrometer spectral line indicates carbon dioxide emission. The 2.7 micrometer region reveals water vapor. The relative strengths of these features tell the story of 3I Atlas's unusual composition. Detection versus non-detection distinctions matter enormously in spectroscopic analysis. A clear spectral line at the expected wavelength constitutes a positive detection. Noise at that wavelength or signal levels below, instrumental sensitivity, represents non-detection, not evidence for absence. The live observing session invitations provide opportunities for public engagement with actual research. Major observatories occasionally offer webcasts during significant observations, allowing viewers to watch professional astronomers conduct real research in real time. These sessions demonstrate the methodical, careful nature of astronomical observation. Image release schedules follow predictable patterns for major facilities. Hubble typically processes and releases significant images within days or weeks of observation. JWST follows similar timelines for high-priority targets. Ground-based observatories often provide same-night availability for exceptional events. Comparison exercises help develop critical thinking skills. By examining multiple interpretations of the same data, viewers learn to distinguish between evidence-based conclusions and speculative extrapolations. Scientific literacy develops through practice in evaluating competing claims against available evidence. The educational value of myth-busting extends beyond 3I Atlas to general scientific literacy. Learning to identify reliable sources, understand uncertainty quantification, and distinguish between correlation and causation provides tools for evaluating all kinds of technical claims. The invitation to direct participation concludes our myth-busting session. Rather than simply accepting or rejecting claims about 3I Atlas, interested parties can engage directly with the observational process. They can follow along with live observing sessions, examine archived data, and compare their interpretations with expert analysis. This participatory approach transforms passive consumers of science news into active participants in the scientific process. The tools exist, the data are available, and the methods are transparent. The only requirement is the willingness to engage with evidence rather than speculation. 3I Atlas offers genuine scientific mysteries worth exploring through careful observation and rigorous analysis. The hidden message we should take from this cosmic visitor is unencoded in radio signals or geometric conspiracies. It's written in spectral lines and orbital mechanics that reveal the authentic story of an ancient traveler from another star. The human imagination, when confronted with cosmic visitors, tends toward the grandiose. Social media buzzes with elaborate scenarios. Redirect 3I Atlas to seed Mars with water and organic compounds. Use gravitational assists to crash it into Mars and thicken the atmosphere. Fragment it into a ring system that could transform the red planet's climate. These ideas capture our desire to play cosmic engineer, but they founder on the unforgiving mathematics of orbital mechanics and spacecraft engineering. Let's start with the energy requirements, because energy is the universal currency that determines what's possible and what's fantasy in space operations. 3I Atlas is traveling at approximately 57 kilometers per second relative to the Sun. This is an enormous velocity. To change its trajectory enough to redirect it to Mars would require an immense change in velocity, or delta V. For context, the delta V required to get from low Earth orbit to Mars is approximately 5.7 kilometers per second. The delta V needed to change 3I Atlas's course by even a tiny fraction of a degree is orders of magnitude greater. We simply do not have the rocket technology to accomplish this feat. The most powerful rockets in existence are designed to launch payloads from Earth. They are not designed to change the trajectory of an incoming interstellar object that is already moving at an incredible speed. The law of conservation of energy states that the total energy of an isolated system remains constant. In this case, the energy of 3I Atlas's motion is far too great for us to overcome with any technology we have now or will have in the foreseeable future. The physics of the universe are not up for negotiation. The time to hit Mars theory is equally flawed. It misunderstands the fundamental nature of planetary motion. The orbits of celestial bodies are vast, and their positions are precisely known. 3I Atlas's trajectory will take it through the general vicinity of Mars's orbit, but Mars will not be at that location when the comet passes through. It's like two people walking on a city grid. Their paths may cross, but if they are on those paths at different times, they will never meet. Our ability to predict the orbits of planets and comets with such high precision is one of the greatest triumphs of modern science. We can predict with certainty that 3I Atlas and Mars will not collide. The distance between them will remain comfortably vast. The idea of using 3I Atlas to terraform Mars is a captivating science fiction concept, but it is not grounded in scientific reality. The mass of 3I Atlas is tiny compared to Mars. Even if it were to collide with Mars, its effect on the planet's climate would be negligible. The energy released by the impact would be significant, but not enough to thicken the atmosphere or transform the red planet's climate. The idea is based on a fundamental misunderstanding of the scale of planetary systems and the energy required to alter them. The artifact hypothesis, which we explored in the previous section, also plays into these fantasies. If 3I Atlas were an alien probe, it would have to be capable of these kinds of maneuvers. But as we've established, there is no evidence to support that claim. Every observation, from the composition of its coma to its trajectory, points to a natural, interstellar origin. The fact that the most plausible explanation is also the most scientifically sound is a testament to the power of the scientific method. It is a system designed to favor evidence-based conclusions over wishful thinking or sensational claims. 3I Atlas is not a threat, it is a gift. It is a rare opportunity to study a piece of another star system, to learn about how planets form and evolve in different parts of our galaxy. The true magic of this event is not in what we can make it do, but in what it can teach us about the universe. We can use our knowledge to learn from it, but we can't use our fantasies to control it. The universe is a vast and complex place, and we are still learning its rules. 3I Atlas is a reminder of this, and a humbling lesson in the limitations of our current technology. The comet, a truly magnificent and enigmatic interstellar traveler, possesses an astonishing amount of kinetic energy, a colossal force that is almost beyond human comprehension. This immense power is conservatively estimated to be around 10 to the 21st power joules, assuming a modest mass for its nucleus. To put this into perspective, the total energy consumed by the entirety of human civilization across a full year is a mere fraction of this, approximately 6 multiplied by 10 to the 20th power joules. This stark comparison highlights the profound scale of the challenge involved in any attempt to alter its trajectory. Any meaningful redirection of this celestial body would necessitate changing its velocity by tens of kilometers per second. This required change, or delta V, represents a monumental engineering feat, one that surpasses anything humanity has ever conceived of or attempted by multiple orders of magnitude. For instance, our most technologically advanced rockets can only achieve a delta V of about 15 to 20 kilometers per second, and that is when launching from a standstill on Earth's surface, not when attempting to alter the path of a rapidly moving interstellar object. The sheer audacity of the idea is underscored by the immense physical and logistical hurdles. The practical challenges are further compounded by severe timing constraints, making any intervention not merely difficult, but utterly impossible. This interstellar visitor, first identified in July 2025, offered a window of only 3 to 4 months before its closest approach to the Sun, a point known as perihelion. Even if we had access to technology capable of delivering the required energy, a capability we demonstrably and emphatically lack, the time available would be wholly insufficient. The process of designing, constructing, launching, and subsequently intercepting the comet within such a limited time frame is a logistical nightmare. Historically, space missions targeting comets have demanded meticulous planning and precise years-long trajectory calculations. The Deep Impact mission, for example, took 6 years from its initial conception to its final impact with a comet. The Rosetta mission required a full decade to reach Comet 67P, Churyumov-Gerasimenko. These missions were aimed at relatively slow-moving, predictable objects residing within the outer solar system, not a high-velocity interstellar guest discovered just a few months before its closest approach. The timeline itself is a fortress of impossibility, a final, unyielding barrier to any redirection effort. Another sobering reality check comes from a consideration of the comet's mass, revealing the unforgiving nature of celestial mechanics. Even if we make a generous assumption that the comet has a 5-kilometer radius and a typical comet density, its total mass would still only be around 10 to the 14th power kilograms. While this seems massive in our terrestrial frame of reference, it is laughably insignificant on a planetary scale. For instance, Mars, our neighboring planet, has a mass of approximately 6.4 multiplied by 10 to the 23rd power kilograms. This means Mars is roughly 6 billion times more massive than our most liberal estimate for the comet. The gravitational influence of such a comparatively tiny object on a planet would be so minuscule that it would be effectively unmeasurable, even by our most sophisticated and sensitive instruments. The idea that a comet of this size could significantly alter a planet's properties or trajectory is a profound misunderstanding of the fundamental principles of gravity and mass. The fanciful notion of using the comet to seed Mars' atmosphere or provide substantial amounts of water and organic compounds is also crushed by the harsh, unforgiving laws of physics and mathematics. The entire atmosphere of Mars has a mass of about 2.5 multiplied by 10 to the 16th power kilograms, even under the most wildly optimistic, scientifically impossible scenarios. For instance, if the comet were made entirely of carbon dioxide, and if its entire mass could somehow be magically converted into atmospheric gas, the resulting increase in Mars' atmospheric mass would be less than 1%. This is a negligible change, far too small to have any meaningful impact on the planet's climate. Similarly, the water delivery scenario fares no better. Mars already possesses substantial water reserves, locked away in its polar ice caps and subsurface permafrost. The amount of water that the comet's nucleus might contain, even assuming an extremely optimistic estimate, would represent a minuscule fraction of Mars's existing water inventory. The contribution would be a drop in an ocean, an insignificant addition to the planet's already vast, though frozen, water supply. The proposal to create an artificial ring system around Mars from the comet's fragments reveals a fundamental lack of understanding of how such systems form and are maintained. The majestic rings of Saturn are not a random collection of debris. They are composed of countless small particles held in stable, precise orbits within the planet's powerful gravitational field. The formation of such a system requires a delicate balance of forces and dynamics. To create artificial rings around Mars would necessitate not only the monumental engineering challenge of fragmenting the comet itself, but also the even more difficult task of meticulously placing those fragments into stable orbits with the correct spacing and dynamics. Furthermore, even if such a system were to be created, it would be a visually spectacular, but climatologically irrelevant, endeavor. Saturn's rings, despite their breathtaking appearance, have a negligible influence on the planet's atmospheric dynamics or overall energy balance. Rings created from the comet's fragments would be a beautiful sight, but would have no measurable effect on Mars's climate or atmospheric pressure. The gravitational assist scenarios, which suggest using Mars's gravity to redirect the comet toward a specific target, reveal another layer of impracticality. Gravitational assists are a well-understood principle of orbital mechanics. They work by exchanging momentum between a spacecraft and a planet. The magnitude of this exchange is directly dependent on the relative masses of the two objects. While Mars could indeed slightly alter the comet's trajectory through gravitational interaction, the effect would be minuscule, measured in mere meters per second, not the tens of kilometers per second required for a meaningful redirection. The fundamental hyperbolic character of the comet's orbit would remain unchanged. It would still escape the solar system, just along a slightly different, though still unbound, trajectory. The idea of using a planet's gravity to change an object's course is sound, but the physics dictate that the effect on a massive high-velocity object like this comet is simply not enough to accomplish the desired result. Amidst all these fantastical and impossible scenarios, there is one genuinely realistic and scientifically valuable opportunity: observing the comet with existing spacecraft. NASA's Mars Reconnaissance Orbiter, China's Tianwen-1, and the UAE's HOPE mission are all ideally positioned to observe the comet from a distance of roughly 29 million kilometers during its flyby. These spacecraft are equipped with sophisticated cameras, spectrometers, and other instruments that were originally designed for Mars observation, but which could provide unprecedented views and data on an interstellar visitor. These observations would provide immense scientific value without requiring any of the impossible redirection, manipulation, or engineering interventions. This focus on realistic scientific observation highlights the stark contrast between what is physically possible and what remains in the realm of science fiction, a distinction that is crucial for the advancement of real science. The universe provides enough authentic wonders and genuine scientific opportunities that we need to invent fictional capabilities to make them interesting. The disparity between science fiction narratives and the harsh constraints of reality illustrates the vast gap between imagination and possibility. Science fiction scenarios often conveniently ignore the immense energy requirements, the severe timing constraints, and the immense engineering limitations that govern all real-world space operations. They often assume the existence of technologies that do not exist and capabilities that violate the fundamental laws of physics. In contrast, real space missions succeed through meticulous planning, conservative engineering, and the setting of realistic, achievable goals. The most spectacular achievements in space exploration: landing rovers on Mars, flying helicopters on another world, capturing images of black holes, are the result of decades of methodical development and incremental progress, not sudden magical technological breakthroughs or the sudden deployment of impossible amounts of energy. This reality check is further supported by historical precedent. Previous proposals for the dramatic redirection of asteroids and comets have consistently failed when subjected to a rigorous feasibility analysis. The energy requirements for such feats exceed our current technological capabilities by factors of thousands or even millions. The timing constraints are utterly incompatible with human development cycles, and the engineering challenges multiply beyond any reasonable solution. Similar grand proposals were floated during the 2017 visit of ʻOumuamua, the first interstellar object detected. Not a single one of these ambitious proposals proved to be technically feasible within the tight constraints of discovery timing and our available technology. The same happened with Borisov during its 2019 to 2020 passage, where practical limitations again overwhelmed any ambitious concepts for intervention. This repeated pattern serves as a powerful testament to the chasm between grand ideas and practical reality. Opportunity cost is another critical consideration for actual spacecraft observations. Even a modest attempt to redirect the comet would consume an enormous amount of resources and would likely interfere with the primary missions of the spacecraft that could otherwise be conducting valuable scientific observations. Mars orbiters have meticulously planned observation schedules, designed to maximize the scientific return from their primary missions. Diverting valuable instrument time and operational resources toward observing the comet represents a significant trade-off that mission planners must carefully evaluate against other scientific priorities. The back-of-the-envelope delta-weight calculation that any layperson can perform for themselves powerfully illustrates the scale of these energy challenges. The equation, delta V equals the natural logarithm of the mass ratio times the exhaust velocity, reveals that changing the comet's velocity by just 10 kilometers per second would require exhaust masses many times larger than the comet itself. This calculation, it should be noted, assumes perfect efficiency and ignores the many practical constraints of real-world propulsion systems, such as their mass, structural limitations, and guidance requirements. Any real-world spacecraft redirection would require even more energy than these theoretical minimums. The conclusion acknowledges that these grand fantastical scenarios are entertaining thought experiments but remain physically impossible. There is undeniable value in imagination and speculation, but this is only true as long as they are clearly and unequivocally distinguished from realistic engineering assessments. The return to practical, achievable science offers far more satisfying and realistic goals. By focusing on understanding the comet's composition, tracking its outgassing behavior, and learning from its unique chemical signatures, we can make genuine scientific advancements without needing to invent impossible engineering feats. The universe, in all its vastness and complexity, provides enough authentic wonders and genuine scientific opportunities that we simply do not need to invent fictional capabilities or impossible scenarios to make them interesting or worthwhile. The script then shifts to address another fantastical fear: the notion that this tiny comet could somehow wake the sun and trigger catastrophic events like solar flares or coronal mass ejections. This fear is a fascinating example of how our perception of scale can be distorted. A tiny spider can induce terror in someone who is unconcerned by a thunderstorm. A small asteroid can inspire widespread panic, while massive hurricanes are often treated as routine weather. The comet, despite being genuinely insignificant in comparison to the sun, has sparked these fears, which fundamentally misunderstand the sun's immense nature and the monumental energy scales involved in solar activity. The sun is a massive, self-sustaining nuclear fusion reactor with a mass of approximately 2 multiplied by 10 to the 30th power kilograms. It constantly generates a staggering amount of energy through the fusion of hydrogen at its core, producing roughly 4 multiplied by 10 to the 26th power watts of power. This energy output has remained remarkably stable for billions of years, with variations of less than 1% over timescales relevant to human civilization. Solar flares and coronal mass ejections are the result of incredibly complex and powerful magnetic field interactions within the sun's atmosphere. These phenomena involve the storage and sudden release of magnetic energy on scales that are immeasurably larger than anything a small comet could ever hope to influence. A comparison of energy reveals the sheer absurdity of these sun-triggering scenarios. A typical large solar flare releases approximately 10 to the 25th power joules of energy, which is about 6 times more energy than the total energy produced by all of human civilization in an entire year. The total kinetic energy of the comet, even when moving at its high speed of 57 kilometers per second, is only about 10 to the 21st power joules, assuming the most generous mass estimates. This means that a single large solar flare releases 10,000 times more energy than the comet possesses in its entire motion. To put it another way, the comet is like a firefly trying to influence a volcanic eruption. The scales are so mismatched that any meaningful interaction between the two is a physical impossibility. The magnetic field consideration adds yet another layer of physical impossibility to the scenario. Solar flares are the result of magnetic field line reconnection events that occur in the sun's corona. These magnetic fields are generated by the sun's internal dynamo processes and are shaped by the massive flows of plasma within its atmosphere. The comet has no significant magnetic field of its own and possesses no mechanism for injecting magnetic flux into the solar system. The material that makes up a comet is primarily ice, rock, and organic compounds, none of which can meaningfully interact with the sun's complex and powerful magnetic field structure. Furthermore, the immense distance between the comet and the sun makes any such influence even more implausible. The comet only reaches perihelion at a distance of approximately 1.4 astronomical units, which is roughly 210 million kilometers from the sun's surface. At this immense distance, the comet would be an infinitesimal speck, subtending in angular size smaller than a single pixel in most solar observations. The Sun's corona, which is where these magnetic phenomena occur, extends for millions of kilometers from the surface. But the comet remains an inconsequential visitor in the far outer reaches of this region. The comet's closest approach to the Sun is still a considerable distance, approximately 210 million kilometers, which places it firmly within interplanetary space. The most generous estimates for the Sun's corona don't extend anywhere near that far, making any physical interaction impossible. The comet's trajectory simply doesn't bring it into contact with any part of the Sun's atmospheric structure. The visual association between comets and solar activity is a common misunderstanding, one that confuses correlation with causation. Solar observatories such as the Solar and Heliospheric Observatory SOHO are constantly monitoring the Sun's environment, and comets frequently appear in their images as they pass through the field of view. This creates a visual coincidence. A comet might be seen in the same frame as a solar flare, leading to the incorrect assumption that one caused the other. In reality, the two events are entirely unrelated phenomena that simply happen to be captured by the same instrument at the same time. A comprehensive statistical analysis of the SOHO database, which contains thousands of comet observations spanning more than 2 decades, has revealed no correlation whatsoever between comet passages and an increase in solar activity. If comets were capable of triggering solar flares, this relationship would be glaringly obvious in the data. The most fundamental objection to any sun-triggering scenario is the complete lack of a plausible energy injection mechanism. There is no known physical process by which a small comet could transfer enough energy to the Sun to initiate flares or coronal mass ejections. The gravitational energy is negligible. The comet's gravitational influence on the Sun is orders of magnitude smaller than the tidal effects of Jupiter, which also do not trigger solar activity. Kinetic energy transfer would require a direct impact. But as already established, the comet passes nowhere near the Sun's surface. Material injection from the comet's outgassing faces similar problems. The few tons of gas and dust released during its passage are a trivial addition to the Sun's environment, which processes billions of tons of material through its solar wind every single second. The comet's contribution is literally less than a drop in an ocean. A safety assessment for Earth further reinforces the lack of connection between the comet and any potential solar hazards. Earth remains at a safe distance of over 270 million kilometers from the comet at its closest approach. The risk of solar storms remains at its normal background level, determined by the Sun's natural 11-year activity cycle, not by any influence from the comet. Space weather monitoring systems operated by NASA, NOAA, and international partners are in constant surveillance of solar activity. These systems are designed to predict and track genuine solar storms that could affect satellite operations, power grids, and communication systems. None of these monitoring systems have identified any increased risk associated with the comet's passage. The illusion created by solar coronagraphs deserves special attention because it produces compelling but misleading imagery. Solar coronagraphs use an occulting disk to block the Sun's bright surface, which allows astronomers to see the much fainter corona and any objects passing through the field of view. When comets appear in these images, they often seem to be interacting directly with the Sun because they are visible in the same frame. This visual impression suggests proximity and interaction, but the reality is that the comet is still millions of kilometers away from the Sun's surface, well outside any region where meaningful interaction could occur. The dramatic appearance of comets in coronagraph images is a result of the instrument's design, not a reflection of actual proximity to solar phenomena. The occulting disk creates an artificial night sky that makes faint objects visible against a dark background, producing spectacular images that can easily mislead casual viewers about the actual spatial relationships involved. The uniform perspective of heliophysics experts dismisses the idea of comet-triggered solar activity. Researchers who specialize in solar-terrestrial interactions, coronal physics, and space weather have found no credible mechanism by which small comets could influence solar behavior. The scientific literature, which contains thousands of papers on solar flare triggers, coronal mass ejection, initiation, and magnetic field reconnection processes, never identifies comets as a significant factor in solar activity. The consensus among experts is clear and unambiguous. Comets are passive observers of solar behavior, not active participants. The educational value of addressing these misconceptions extends far beyond this single comet. It helps develop a broader scientific literacy about the immense scales of energy, the crucial distinction between cause and effect relationships, and the importance of quantitative analysis in evaluating extraordinary claims. Understanding why this comet cannot trigger solar catastrophes helps people develop a more intuitive grasp of astronomical scale and the relative insignificance of small objects in the grand cosmic environment. These concepts are broadly applicable to other astronomical phenomena and are essential for distinguishing between genuine risks and imaginary threats.